Tutorial. My name is Fernando, and I'm going to be the first lecturer this morning, but the three of us from the IPython project are going to be taking turns. So Brian Granger and Min Reagan Kelley up front are also here, and they'll be taking relief from me a little bit later. And we also have in the room two other members of the project, Paul Ivanov in the back, who is a grad student at UC Berkeley working with me, and Zach, I'm sorry, Zach, your last name? Zach Saylor, who is a student with Brian Granger at Cal Poly San Luis Obispo. All four of us will be available to help you. If you get stuck on anything, just raise your hand and the nearest one of us will come and try to give you a hand. Needless to say, feel free to interrupt us while we're speaking. This is meant to be very interactive. Before we dive into our tutorial, I'm going to take a couple of seconds to show you a few slides that were sent to us by Stuart Williams, your tutorials Uber coordinator for the entire conference, who asked that we pass along the message that the conference still needs volunteer help for a number of tasks, and there are a number of fairly low commitment opportunities for you. There's ways for you to help, bagging swag on Thursday, helping at the registration desk anytime. But on Friday, you meet lots of people. And there's a couple here. If you go to that URL, bit.ly, PyCon volunteering status, you can see exactly what they need and how you can help. So if you can spare a couple of hours to give a hand with one of the tasks for the conference, please do so. OK, so we're going to get started with a very quick introduction and quick check of installation status, so that we've been doing that kind of informally for the last 20 minutes. We're not going to really have slides per se. This is going to be all very hands-on and meant to get you really exercising your fingers and building muscle memory and learning how to use the tools. So the only introduction that I'm going to give really to the project is straight off of the website. And what I want to point out are a couple of kind of broad ideas. The first one being that IPython is really a system for interactive computing, understood in a very broad sense. Yes, it began as a command line replacement for the default interactive Python shell, but the scope of the project has grown beyond that. And in reality, today, we think of it as an architecture for interactive computing that allows you to use any language for which it's sensible to be used interactively, so that you can drive, and we're building an architecture to allow you to drive actually processes that are implemented in other languages. We already have a Ruby backend for the IPython architecture. We're building a Julia backend. There's a MATLAB backend in the planning. There's an R backend in the planning. So the idea really is to provide the interactive workflow that is very common and very necessary in many fields of computing through the same common messaging architecture and with the same protocols and formats for storing those interactions, which is the notebook format that we'll come to later. And so, yes, if you are a dyed-in-the-wool Python programmer who does nothing but Python, IPython will continue to serve you well. But if in your work and your needs cross language barriers, there's actually a chance that some of the tools we have here will be useful in that regard too. And we don't have a ton of time to dive too much further in that direction, but it's important for you to sort of understand the scope of the project. And so what IPython provides are, first of all, the classic interactive shells that we've had for a long time at the terminal, and we also have a Qt-based shell that I will very briefly demonstrate that is basically a terminal on steroids oriented towards interactive computing. We have a browser-based notebook that we'll be using extensively throughout the presentation that you'll see a lot. IPython has support for synchronizing with event loops, and therefore synchronizing interactive applications with GUI applications without blocking the interactive control. And we'll see how to do that. That can come in very handy in many situations. IPython is very easy to embed in your own Python codes, so that you can have either an interactive shell pop up in your code or actually an interactive network controlled engine, and we'll see how to do that. And finally, high-level tools for distributed and parallel computing that can be used interactively as well. The emphasis is always on the I, right? The I in IPython is for interactive, because all of the tools we're building are meant to be used with a human in the loop. So if you go to our website, the installation link should have given you the instructions that you needed. Hopefully by now everyone is okay with that. I want to point you to a couple of important links. We won't have time to dive into them in detail, but at least I want to highlight them for you. And that's these two links, our example collection and our notebook gallery. Our notebook gallery is actually a wiki to which you can contribute. Which is a list, a growing list of interesting things that people are doing with the IPython notebook and notebooks that they're building in all kinds of areas and fields. And because this is a wiki, you can add to it. I'm not going to go over all of them, but just to give you a very brief taste of what one of them looks like. This is the first chapter of a book on statistics and Bayesian inference. And this is what a notebook can look like. It actually looks like a book with math, with very nice typesetting. But you have code, you have mathematics, you have code, you have the figures right there. And every one of these notebooks at the top has a download link that lets you download it and execute it right away. These things are all powered by a web service called NBViewer, which is part of the IPython project. And NBViewer is effectively a Heroku-based app that will convert your notebooks and put them up on display in HTML. So what this enables you is to share notebooks with others, so that you can put a URL here of any publicly available notebook and share it. And that's how the gallery is basically a long list of links to NBViewer-powered renders, and the server re-renders the notebook when it's requested with a short caching period, so that as people update their things, whenever you visit them from here, you get updated versions. And one of the important links in here is actually our collection of notebooks from our official documentation. This is a collection of notebooks that will cover some of the things that we're covering here in a lot more detail and with a lot more explanation in depth. So I strongly encourage you later to visit these. And whenever you click on any one of these links, this is part of the official IPython repository, but whenever you click on any one of these links, what you get is precisely the rendered version. If the network cooperates, what you get is precisely the rendered version of that particular notebook, so that you can read it and study it. And so these are links that are useful to know about. Okay, so at this point, everyone should be set and ready to go. Again, the tutorial location is IPython in depth on GitHub. This is where the materials are. And you can either clone the repo or you can download this zip file and unpack that zip file wherever you want it to go. Is anyone having a problem? I'm sorry. Okay. So, and we have it on a USB stick if somebody's having connectivity issues. So the first thing that you'll want to do, and now I want you to follow with me, is go to the directory. Whoops. Go to the directory where you have the unpacked this zip file and cd into the notebooks directory. For those of you on Windows, you want to be using the command.exe shell. If you have a git bash shell, it may not have your paths configured correctly. So use command.exe. On Linux or the Mac, just go with the terminal and simply type IPython notebook. Okay? And if you type that, something like this should happen, where with no error messages, and then it will tell you that the notebook server is running on your local machine. It's not listening on a public port, so don't worry about security. We'll cover that later. So it's completely confined to listening on your local machine only, and on that port by default, and it will most likely actually open the browser. In my case, I have it configured not to open it by default, so I had to open it myself. And once you open it, this is what you will see. And so I am not going to cover in depth what all of this is right now, because the in-depth usage of the notebook is going to be the second part of the tutorial. What I'm going to do is we're going to start using it to see where does IPython go beyond plain Python. Because what IPython does is really go a little bit beyond what the plain Python experience is. And so if you click on this notebook, IPython Beyond Plain Python, you should see right here what our first notebook is. Can everyone in the back see? And is this font size going to be okay for the recording team? Or should I try to crank it up further? Obviously, the more we crank it up, the more space we lose on the screen, but if it's unreadable, then there's no point. It's okay, as is? Okay. Actually, Min, excuse me? Yeah, that would be actually probably a good idea. Does anybody know how to dim maybe the front lights? Because it is true, they're washing the screen out a lot. Min, do you have it rendered on an iPad, this one, by chance? Do you think you could get it off of NB Viewer? And maybe I can use it as a cheat sheet. So what I want you to do is type with me. Yes? Paul, can you try to help him? Yeah, Brian and Paul will give you a hand. Back to where I'm going to restart what I was doing. So I am in the directory where the notebooks are. And what I need to run is IPython notebook. And that will give me something like this, which then I can go and open my web browser to this dashboard running on my local port. And so the first thing that I want to go through is the notebook that basically covers where does IPython go beyond the plain Python experience, okay? So IPython is meant to let you do everything you would do in a Python shell is valid Python. So if you type normal code, it should execute just like Python code executes. But there are some things that IPython does that are not valid in a normal Python shell. And we're going to try to understand what is it that IPython offers beyond the plain Python shell. So when you're in the notebook, if you type a block of code, like say print hi, in order to execute code, you hit Shift-Enter. So that's how you execute code in the notebook. So I want you guys to follow along with me and basically start getting used to the muscle memory of typing code in these cells and executing it as we go along. So Shift-Enter is what executes code. And the reason why it's Shift-Enter is because these little areas are not like a terminal prompt. They're more like a mini text editor. So you can put more code in here and hit Shift-Enter, and it will execute all of the block as a single chunk of code. So you can also execute with Alt-Enter. I'm sorry. Alt-Enter is a newer feature for those running the development tree. You can also execute with Control-Enter, which does not move the cursor in case you simply want to try something here and replace it later with something else. If you run Control-Enter, the cursor stays in the current cell. With Shift-Enter, it moves to the next cell below. So that's code execution, and that'll be the same as plain Python. Now, if you want help, IPython has added a special syntax which isn't valid Python, and the most basic version of that special syntax is to just type question mark. So when you type question mark, what will happen is you get a little pager here at the bottom. And this pager basically shows you additional information. And this will work the same thing in the notebook. If you're in a text terminal, it'll use the system pager, but it'll always try to find a way of displaying information for you. You can dismiss this pager by clicking on the divider. And so when you type simply question mark, IPython will give you a very basic introduction to what it does. Okay, this is basically what does IPython do, and you can drag this divider if you want to read it a little bit better. So I'm not going to read through it because the whole point of this meeting is to cover some of this for you, but a simple question mark gives you information just about IPython itself. But the question mark operator is actually an operator that you can use at any point. So if I type import collections, and then I want to find out about what is the name tuple object, if I type collections.nametuple question mark, what IPython will do is actually go and dig, using the fact that the language is highly introspective, it will go and dig into the collections name tuple object, and maybe I should just full screen this so that we have a little bit more space. It will dig into the collections name tuple object and show me where was it defined, what is the file, what kind of object is it, what is the file where it was defined, what is the calling definition of the object if it's a callable object. And furthermore, it will show me the doc string of the object. So this is one of the reasons why in the scientific Python community where IPython was born, we tend to put so much emphasis on high-quality docstrings. The standard library has a very uneven coverage of docstrings. Some of them are pretty good. Some of them are very minimal or non-existent. And part of it is because we use this a lot. As we're working, we just type object question mark, and right away it tells us what's going on. And if you add 2 question marks, IPython will try to actually dig even deeper into the object and give you more in-depth information. So if I ask double question mark, instead of giving me a summary of the main properties of the object like type and signature and docstring, IPython will actually show me the entire source code for the object, and it'll syntax highlight it. So now when I type collections.counter double question mark, then what we have here is the entire source code for that particular object. And you can actually ask for the source code of any specific object. So for example, the counter, the most common method, if I had asked for counter.most common instead, then I would get the source code just for that method, right? So it's a very useful way of understanding, for any object for which the source code is available, it's a very useful way to quickly learning about your libraries. The way I learn about most libraries is not by reading their documentation, is by just asking with question mark for the methods and functions that I'm interested in, that quickly can learn their signatures and see their code and just move along. So it's trying to be very effective in its workflow. And finally, there's a way of using the question mark for querying namespaces. So if you want to find what variables do I have currently defined that have int in their name, you can use the kinds of globs that you use at the shell, like ls star, but with a question mark, and then what IPython will do is find any names that match that pattern. And you can do this within a namespace, or you can do it at the top level namespace. So it's a very useful way of digging into big libraries that you don't know to find bits and pieces of information. So this is basically anything that has the letters I and T in my namespace. These are the things that have that. So these are the basic tools for digging into objects and using the IPython introspection machinery. If you want to learn a little bit more about all of these special syntaxes, you can type at any point %quick_ref, and quick_ref will open a quick reference card of all of these special syntaxes. I'm not going to go over them. We're not even going to cover all of them today, because IPython has a lot of syntactic tricks that are really meant to kind of speed up your workflow. But at any point, if you type %quick_ref, you will see a little help page like the ones we're seeing with a quick reference card that is it's basically like a cheat sheet for the system. Okay? Any questions at this point? So, yeah. Excuse me? They do up to a point. The problem is we can't. There are no hooks for finding the source code of a native code object. So you will only get very basic information, the kinds of things that the inspect machinery can find, but not the source code. With one exception, for Python-based extensions, we can dig in. If the source code is still available for Python-based extensions, we can find a little bit more information. But for normal extension modules, it won't, because it's just binary. And if it was compiled, I mean, Python doesn't leave source information behind for us to find. So there's just not, it's a binary blob on disk, and there's nothing we can do about it. It will give you the doc string if it has it. It'll give you the high-level information like name, docstring, from where on the file system it was imported from. So you'll get a little bit, but you won't get as much as with pure Python. Any other questions? All right, do interrupt at any time. So when you're working interactively, the basic workflow, as I said, is the same as Python. You type 2 numbers, you add them together. The Python shell always creates a little variable called underscore. We still have that same variable. However, you can, if you want, you can suppress output by putting a semicolon at the end of a line. And if you put a semicolon at the end, no output is generated and the underscore variable isn't updated. So in this case, underscore is not 30, it's still the old 22. The reason why that's useful is because there are many libraries that when they do a computation, they also generate a lot of extraneous extraneous results, especially things like plotting libraries, which for some of us are very important. They also produce a lot of stuff. So we often get into the habit of putting a semicolon at the end of the last line so that we only get the figures, but not the actual return values of the underlying object. So it's just a useful trick to know when you're building, especially when you're building these documents where you just want maybe to compute something and leave the figure for people to see, rather than leaving a bunch of internal object pointer addresses that aren't meaningful. Now, these prompts out here on the left that say in and out, they are obviously meant to give you cues of what you've been doing and in what order you've been running code, but they also actually exist as variables. So we do create an underscore variable, but we actually create underscore and a number for any variable that I have created. There is actually an underscore in that number automatically created for you. So underscore is the previous one, but underscore and the number will give you whichever old one. The reason why that's handy is if you've computed something that took a while to compute and you have that result, but you forgot to assign it to a variable, no matter. As long as you can read which number it has, you know that there's underscore and that number auto-generated for you. And they actually are also stored in a variable called out with a capital O, which is effectively a dict of outputs. Now, the reason why we create the automatic underscores is because you might clobber the out variable with one of your own variables that you call out, and so we have these automatic ones. And we have a single underscore, 2 and 3 underscores actually for the last and the two back. These things come handy when you're just doing quick calculator style work. And similarly to the outputs, we have input variables. So similar to the output, we have in variables and underscore I variables, which means that you can manipulate everything you've done with your inputs and your outputs programmatically. You can re-execute based on these input lists or output lists. And there's a command called %history that will give you that will show you what your history is, and it has a number of options, such as, for example, if I simply type history, it'll show me everything that I've done so far. It'll print my history. It's useful if I want to copy it to, if I want to copy into a text editor, for example. But I can say, show me my history with line numbers. If I do -n, it'll print it with line numbers. Question?
Source syntax you use, is that used only interactively, or would you ever use that in code?
No, that's used only interactively. So that's a very good question. That underscore syntax only makes sense interactively, and the reason why it only makes sense interactively is because those variables are created when sys.displayHook triggers. And sys.displayHook is something that only triggers when Python is being used interactively. When Python is being run in code, code execution doesn't trigger sys.displayHook because the code objects get compiled with a different set of flags internally. And so it's actually something that hooks pretty deep into the Python machinery itself. And so those things don't even exist. When you're running a script by itself, those things don't even exist at all. Good question. Yes?
When using just a shell like outside of a notebook, that doesn't make sense here, but the history, is that preserved like over sessions?
Yes. So if we ask here, as always, the question mark, right? So history question mark. And history shows you how you can actually access the history of other sessions. There's a special syntax to access the history of other sessions. And in fact, the entire IPython history of any session you've run, even if you have multiple terminals open, is logged into an SQLite database. And you can actually open that database and browse it. So the history command lets you grab the history of other sessions with this syntax. But you can actually go and open that SQLite database in your .IPython directory. You can open that SQLite database yourself and actually browse it. We don't really have any UI for kind of more beyond this, but the database is there and it logs everything you've done in any session you've ever used. So as a quick exercise for a couple of minutes, I want you to write the last 10 lines of your history to a file named log.py, and I'm going to give you just 2 minutes to do that. How would you find out how to do it? Well, question mark. Question mark tells you how to use the system, and then in the explanation, the information should be there for how do I get the last 10 lines and save them to a file. Here, the history tells me that -f lets me pass the file name. And if I look here, -l takes numbers. If I read here, it says -l gets the last n lines. And -f lets me give a file name so that instead of printing to the screen, so if I say, give me the last 10 lines and write it to log.py, then this information should have gone to the file log.py. Can you use magic? Up to a point. So you can assign to a magic. You can assign the output of a magic. We'll see that in a minute. You can assign the output of a magic, but that's about it. But I've been using the history command with this %. Right now, up until now, I haven't really explained to you exactly what that % means. There's a little bit of a bootstrap question on exactly in what order do you explain things. And so I've been abusing your brains by using %history without really telling you what it does, what that % is for. We're going to cover that in a minute, and then we'll talk about that. Whoops. Okay, what happened here? Do we have a bug? Excuse me?
Come before the -l argument?
That's odd. Indeed. And I don't know why. We should fix that. You should file a bug for that, because that's not nice, that those arguments are order dependent. So yes, indeed, and I guess yesterday when I did it, I by accident did it in the right order. So we pass it a file name, and then we tell it to give us the last 10 lines. And here I can see that that file exists, and it has those 10 lines. And what I did there was I called the cat command with an exclamation sign. That gets us into the next topic, which is that in IPython, whenever you type exclamation, that goes as a system call to the underlying operating system. And if you're on Windows, it'll run a Windows command. If you're on Linux, Mac, or OS 10, it'll run a Unix command. And the reason for that is because we really, when working interactively, especially in the kinds of jobs that we do, which is a lot of data analysis, a lot of not so much doing software development, but using Python as a tool for analysis, we very often need to know what's on our file system, what files do we have. And so quick and easy access to the underlying operating system is very, very important. And we've taken a few liberties with the language syntax, such as not only can you call exclamation and call a single command, you can actually assign the output of that in this way. So if I say files equals exclamation ls, then that will capture the output of that command into a variable called files, and that files is a list. And furthermore, you can actually not only grab the output of shells into Python variables, but when you call commands with an exclamation, you can actually expand the value of Python variables. So if I say echo $files, that actually will expand into an echo call at the shell, the value of the files variable. You can see how this becomes very, very handy quickly, because you can mix and match Python code to do complicated logic with system calls very easily. Not the kind of thing that you want to be writing for long-lived production code, but it's very useful in short interactive snippets to do the complicated. I can never remember how to do a loop or logic in the shell, but there are some things where you do want to call a system command. So I do all my complicated logic in Python, compute my variables, and then simply make the calls by replacing the values I need. And not only can you call simple, so with a simple $, you can resolve variable names, but if you use the Python formatting syntax with braces, you can actually call arbitrary expressions. So here, I am actually calling the expression file0.opper, which is a Python expression, and resolving that with braces. And so it lets you actually do pretty fancy things in terms of having a hybrid workflow where you do the heavy lifting in Python and then you call out to the shell as you need it. And you can put these exclamations in the middle of a nested loop if you need to. Okay? So this is the first important syntactic deviation in Python, in IPython beyond Python, which is the exclamation character. It's a sigil that says go to the OS. The second big one is called the magic function system. And now we're really going to talk for a couple of minutes about what this % business is. So this percent business is a set of commands called magic functions, and this name was inherited when I started IPython when I was a grad student. IPython was the merger of 3 code bases, some code that I had, code from a grad student at Caltech called Lazy Python, and code from an oceanographer in Germany called IPP, short for Interactive Python Prompt, and his name is Janko Hauser, and IPP had these these magic function method calls to do OS style things. So I inherited that, and we've kept the name since 2001. That's why they're called magic functions. Janko called them that way. I don't know why he called them that way. But the point is, the magic system allows you to define commands that have much more of a command line style interface. You don't have to quote things. You don't have to put parentheses. You don't have to put commas. It's simply dash flags for arguments and spaces. So it's a very command line style interface, which is handy when you're typing quick things interactively. And the second important point is that they live in a namespace which is orthogonal to your Python variables. So they provide basically a control mechanism and a utility namespace for things that don't collide with code you're running. So as you run things, your code may define new variables, you may have Python names. These control names live in a completely separate namespace, and because there's a special percent syntax, you can always know that you can call these control commands and they're not going to clash with names that you may happen to have defined, okay? So if you simply type %magic gives you a summary of the magic system, oddly enough, and it basically summarizes what the system does, and it gives you a list of all of the magics that are currently defined in the system. For any magic, you can always type question mark, just like we did history is a magic, and so with question mark you can get its docstring, and we've tried to be pretty good about giving very detailed docstrings for all the magics and what arguments they take and so on and so forth. You can define your own magics. We're going to cover that later today. So the system is meant to be completely customizable and extensible. And IPython ships with a bunch of them, but you can create your own. So a very simple, handy one is %timeit. And %timeit simply calls the Python timeit module. But calling the Python timeit module correctly requires that you import a couple of things and do a few other things. If you simply do %magic, %timeit, and an expression, it'll use the Python timeit module on that expression. Very, very handy when you're having a debate on a mailing list about the performance of a little code snippet. You just do timeit, and you can copy and paste, and you're done. Now, in addition to a single %, recently in IPython, which has existed in IPython for a long time, we recently introduced double %. And the notion of double % is what we call a cell magic. So when we were working only at the interactive command line, everything was very line-oriented at the shell. But now that we have environments such as the Qt GUI console and the notebook that lets us type entire blocks of code, we've extended the notion of a magic that doesn't apply just to what the command you're typing on that line, but that applies to the entire body of that cell. So if you type double %magic, then what that does is it will execute the entire chunk of code, whether it's these 2 lines or 100 lines of code, and it will give you a timing report on the entire block of code, okay? And we do have a number of magics that use the double % syntax to transform how the entire block of code is executed. So, and you can define your own. So the magic system, in summary, has 2 styles of usage. Single % applies to just what's on that line, and we call them line magics, and double % applies to the entire block of code. Now, because the single % ones apply only to the current line, you can actually use them in a loop or in other blocks of Python code, just like you could put exclamation in the middle of another chunk of Python. So here, let's say that I want to run some code and then do timeit on a specific expression that depends on that context. Well, I can keep calling timeit within my block, and it will actually, as it goes, what happens is we actually translate all of the input code. Before we send it to execution to Python, we translate the block and we generate valid Python syntax. We didn't hack into the interpreter. We simply transform this into the equivalent valid Python syntax that makes the underlying function calls. Okay? And as I said, the double % ones can actually transform what you're doing in arbitrary ways. Because what will happen, and you'll see how to write your own magics later, is the magic actually gets the block of code as a string. It can do whatever it wants. It doesn't have to call exec on it. And so, for example, the magic double % bash actually calls that chunk of code as bash. It will call bash. For those of you on Windows, this one won't run, but you could have the equivalent one with command.exe. In fact, we have one, I think it's called system. And so the point is you can actually, with this, you can define magics that mix and match languages. And we have an entire body in our examples collections. You will see a notebook called script magics that actually shows magics that do Ruby, Bash, Perl, and capture their output. And you can do fairly elaborate things so that as you build a document, if you're doing a bunch of code and then you do need to do a little bit of heavy-duty OS stuff that you already had Bash code for it or chunk of Perl or Ruby, you can put it right there and you can keep a single integrated document that weaves them all into a computational workflow. Okay? So, for example, there's a useful one called $file. All that $file does is you give it a file name and then the rest of the body of the cell will be written to disk as that file. So if I type $file text.txt and I write a bunch of text here, when I look at text.txt, that's exactly what is in there. Why could this be useful? Well, maybe you do need to generate a file on disk from a notebook you're running on a remote server, and you want to generate a snippet of code on disk because some other command line code is going to execute it and it needs files on disk. Well, for small snippets, you can do it this way. And yes, you could put everything into a string and call the open file in write mode. Well, we do that for you, right? And we do it by simply putting $file, okay? And as I change the code, if I re-execute it, it gets overwritten, and the content is right there immediately. So this is a destructive operation to generate immediately that content on disk. So the magic system, as I said, is fairly extensive. There's a magic called LS magic that tells you which magics are currently available, oddly enough. And so LS magic simply tells you the names of all the existing magics. As you see, there's quite a few of them, and we tell you which ones are line magics and which ones are cell magics. And it also says that automagic is on, which means that the % prefix is not needed for line magics. What that means is that if you're simply typing in a single line by itself, obviously not in the middle of nested code because we have no way of disambiguating, but in a single line of code, you could omit the %. These days in the notebook, I never do that, but it is handy when you're just typing at the command line at the terminal, and it's completely throwaway interactive work than to not just spare yourself the %. Honestly, these days, I don't really rely too much on this anymore, but back when all we had was the interactive terminal, it came in kind of handy. So as you're running code, any other questions? Yes?
That if you type like ls and cd without the exclamation point, it also does that. So how does that work? Is it just...
So because there's a cd magic. Yeah. CD is a magic. And so now, ls is actually a special case. It's not a magic. It's what's called an alias, which is actually a separate code path that calls system aliases. But now that our magic system has been revamped, the reason why I didn't talk about aliases, ls actually doesn't take a %. The reason why I didn't talk about aliases is because we're in the process of deprecating them, and we're going to unify aliases under magics. Because it's yet another special case, and it isn't really necessary. And we recently figured out that we could completely we can get all the functionality of aliases, and it's easier to explain. There's only two special funny syntaxes: exclamation for the operating system and % for commands, and that's it. Rather than this third weirdo other special case. And so very soon ls is going to take a % as well. So if you paste code, we do a few other things that are purely for convenience. You see a tutorial or you're having a discussion with someone online and they paste a bunch of interactive code. If you actually paste code like that from a Python shell, it'll run correctly. So what we do is we'll strip it out of all that gunk in front and we'll run it correctly for you. And same if you paste from an IPython shell that has the IPython numbered prompts, we also do the same thing. We will also strip them for you. The reason for this is just to make your life sort of easy while you're copying and pasting examples in discussions and whatnot. So how do you, as you're running code, one of the things that happens most often is that you have errors. So another thing that IPython tries to do is give you better error information than the default Python shell. So let me write a little file called mod.py that defines just 2 functions. And I did it with 2 functions just so I have a little bit of a stack to show you the depth of the stack. And so now if I import this module and I call the g function with 0, the g function calls f of y plus 1, and f calls 1 over x minus 1. So I get a division by 0. And this is what the IPython tracebacks look like. So they are more informative than the default Python tracebacks. They show you a little bit more code context around where things happened. When you have input that comes from IPython itself, instead there's no file. You're working interactively. So what you see is IPython input and the prompt number, and then a hash identifier so that we don't get collisions and some of the internal caching works correctly. And then the frames in the stack that come from files, you'll see the complete path to those files. So these tracebacks are syntax highlighted. They're a little bit deeper. They have arrows pointing to the individual lines. They're a lot easier to read than the default Python tracebacks. But you can also change the mode of exception reporting. There's a magic called X mode for the exception mode. If you say plain, then you get these plain tracebacks that are much more similar to the plain Python ones. They're just basically the Python ones with syntax highlighting. And you can also say verbose. And if you say verbose, what happens is we actually introspect your entire call stack. And we give you all of the values of every variable at the calling point. So the reason why this is not the default is because this can get expensive. Right? It can get expensive to go on every point in the stack and actually do full introspection, get all the string representations of every variable and print them all out. So it's not the default, but it's a handy way of understanding what's going on with your code if you want it. The default one is X mode context. That's our default, which is kind of this balancing point between giving you more information than Python does by default, but not doing the potentially expensive operations. Okay? So there's one more magic that is very important for many of us, maybe not for all of you, but I want to mention it, and we're going to talk a little bit more about the rest of it in a minute. It's the PyLab magic. The PyLab magic, what it does is it loads NumPy and Matplotlib, which you all have installed, because by installing EPD, it comes with NumPy and Matplotlib. So PyLab inline, what it does is it configures NumPy and Matplotlib to plot with inline figures, so that when Matplotlib creates figures, they come back to the notebook and they're shown inline along with the document. Rather than popping up a window on the side, they come directly into the document window. The reason why this is useful is because if you're starting it on a remote server, you don't want a window popping up on that remote machine. You want that plot to come back to your browser that you're accessing through with which you're accessing the notebook. So if I type this bit of code, that produces this plot. And what I did was I held on to the figure object as a variable called f, which I can redisplay later if I want to. So f is my figure variable, right? And I'm displaying it later. And the reason why I held on to it is because I want to show you one more thing, which is how is all of this working? Right now we've been typing code in a web browser, right? How is this working? Well, what's happening is the web browser is connecting to a little web server up on 127.0.0.1 port 8888. That's a Tornado web server that's running. And that Tornado web server is communicating to a process in the back which is really executing your Python code. That process is what we call the IPython kernel. And so that process is sitting there talking to the web server over 0MQ, and then the web server is relaying that information to your web browser, translating the 0MQ traffic into WebSockets traffic, which is why you need a fairly modern web browser that supports WebSockets for all this to work, i.e. Chrome, Firefox, or Safari, not Internet Explorer before 10. I think IE 10 works. And so we have the client running in the web browser. We have a server process here in the middle translating traffic, and we have our kernel, that's the guy who's really executing the Python code in the back. That architecture is actually very, very powerful, and we're going to see how we get a lot of mileage out of that design. You can actually talk to that thing in the back yourself, to that remote kernel in the back. So if you type %connect info, %connect info is a magic that gives you the connection data on the ports that that thing in the back, that kernel in the back is using. And it not only does it print it for you so that you can copy and paste it into a file, but if you're on the same machine, you can actually connect to that by using you can actually connect to it with another client by using the -- existing flag and this file path that it will print for you, because this information was written to disk automatically. So basically you have a token that allows you to connect to that thing in the back, and other clients can connect. So I'm going to show you, this will probably not run for most of you. I'm only going to show it to you for a second because we didn't want to deal, we've had enough hassles installing just the basic stuff. If we ask all of you to get Qt up and running, we'll be here until tonight. So this is only something that I'm going to show you for a second. If I type %Qt console, what this will do is it will open, I need to not full screen my thing. Here it is. So what this did was it opened an application which is our IPython Qt console, but it's actually connected to the existing kernel that's already up and running. So remember how I had my F figure? There it is. So this is something that looks like a terminal, but it's actually a soup-top GUI widget written in Qt, developed by Enthought, that has the look and feel of a command line terminal, but actually can do things like multi-line blocks, syntax highlighting, and embedding images and whatnot, because Qt has a fairly sophisticated rich text widget. So this thing is automatically what the %Qt console does is it basically gets this connection information and then opens a Qt console process with those flags automatically for you, so that you have a second client talking to it. And just to show you, if I type, we also have a terminal client called the IPython console, which is basically the old-fashioned IPython shell, but running in the console. I can connect to the exact same process, and then if I type F, I get my same figure. Now, in a terminal, I can't display an inline figure. This is the real terminal, right? This is my shell. I can't display it. Well, IPython says, okay, F is a matplotlib figure. It prints the classic wrapper of the object. But now we have three things talking to, if I say now F is 100, F becomes 100. If I go to the console, now F is 100, right? These three things, and the notebook now, F is going to be indeed 100, right? These three things are all talking to the same process, so you can access that kernel through the notebook, through the Qt console, or through the terminal console client. Paul Ivanov has written a Vim client that uses the same protocol to talk to the kernel via Vim. Microsoft, Dino Wieland, who will be here, and Shirok Mortazavi at Microsoft as part of the Python tools for Visual Studio, developed a Visual Studio plugin that talks to the same process using the same protocol. There's a fellow in Japan, Takafumi Arakaki, who developed an Emacs client that actually displays full notebooks, but in Emacs. So instead of working with your notebooks in the browser, you do it in Emacs, and there actually is WebSockets support in Emacs and Lisp. And so it actually talks the full protocol. So it's important to understand that this architecture is actually, it's a little complex, but it actually is very powerful, because as I was saying earlier, now that you see how this all works, you can see why somebody could write a kernel which is not running in Python. It's actually a kernel that is running in Ruby or in R or in MATLAB or in Julia or in whatever else. As long as it speaks these protocols, it can run, and the same console, notebook, and Qt console clients will be able to connect to it all the same, as long as they speak the right protocol. Okay? Any questions? Yes?
The JSON file is sort of the configuration.
It's the port connection information, yes.
And the protocol or specification for actually conveying to the kernel, this is what I want you to do with this request, and triggers all the data associated with that whole document.
Yep. So that's here. IPython.org, oddly enough. Docs. That was a little slow. So if we go to our docs are organized really badly. We're in the process of cleaning this up. But right now, in Developer's Guide, there's a page called Messaging in IPython. This page is exactly that description of, it's a short diagram of the model, and it's a description of all of the messages that can go through with how they need to be formatted and what payloads they can carry. So it's exactly a spec of the entire protocol.
Authorization kind of subsystem here, or is it sort of assume that this is only going to be open on a local port and you know,
We're going to cover that later today. Min is going to go into how you set it up in a security. If you want it to run on the public port, how do you add layers of security? So that, I mean, right now it's running over plain HTTP completely locally, and it's only listening on local ports. But Min is going to cover more of that. Okay? Any other questions? Yes, in the back.
If I have a server written in Python, can I embed the kernel with it in the cache console?
Yes, if you give me 5 minutes, I'll tell you how. That's the next section. Any other questions? I didn't not plant him. Okay, so the next question, the next part is going to be terminal use. It's the notebook called terminal usage. And it's basically a couple of things that you tend to do a little bit more in the terminal. I have them in a notebook just to organize the presentation, but I'm going to be switching a lot out to the terminal. Let me go back to my terminal here and close this client. So let's say that if I have a file called, say, script.py that has these little variables, when I'm working in the notebook, I would just put that as a cell of code. But if I'm working in the terminal, okay, sorry, let me go to where I was. Script.py, yes. So if I start the normal IPython, if I'm working at the terminal, not in the notebook, and I have that script file, the way that I would normally work, and it's still useful to know about this because you may be working in a server where you don't want to set up the notebook for whatever reason, you're just SSHing in and you want to run a little bit of code and analyze something, and you have Vim open on one or Emacs open here and just a shell window. What you would done is you would say run script.py, right? %run is yet another magic, but it's a magic, it's a magic that is most used. You can use it in the notebook or you can use it at the terminal, but it's much more useful in the notebook, in the terminal, because in the terminal you can't really write a block of code conveniently. So the workflow is much more write scripts in a file, run them from the command line, and run is basically exec file on a lot of steroids. And I don't have time to go into everything, but run can be invoked with, for example, -t, so that it summarizes timing data. After the run, it has a -p to run under the control of the profiler. So it gives you profiling information after the execution of your code. It has -d to run the code under the control of a debugger, of the interactive Python debugger. So it has a bunch of flags. I encourage you to look at it. The model of run is that once you run the code, the variables defined in the script, so cat script.py, X, Y, and Z now become defined interactively. So the idea is you run a script, it executes the code by itself, but then the variables that were declared in the script become available interactively, which is very handy because you run a chunk of code, but then later you want to play with those things a little bit more. You want to plot them, you want to print something. So they basically get loaded. It's executed in an empty namespace so that the script will run as if you had run it by itself, so there's no dependencies with IPython, and it doesn't get polluted by your variables. But when it finishes, its namespace gets loaded into your interactive namespace, okay? So it's a very handy command to know about. And very importantly, there is one thing that you cannot do yet in the notebook because we haven't finished implementing support for interactive input from the sub-process. So this is the one thing for which you still need either the Qt console or the terminal console. This works in both Qt and the terminal. It doesn't work in the notebook, which is if you run a script that has throws an exception and you want to debug that exception interactively, in the terminal or in the Qt console, after any exception has been thrown, and even if more execution has happened, as long as there is an exception still kept in memory, you can type %debug. And %debug will drop you into the interactive debugger. This is basically a slightly souped up version of PDB, where you can do L, and you can do up and down, and you can print what is X. Right, this is PDB. I don't have time to do a tutorial on PDB right now. The point is I want you to know that while you're working here, you can drop immediately after any exception and go. So rather than putting lots of print statements or needing a GUI debugger, you can just do %debug whenever your code throws an exception. We would love to have this capability in the notebook. We will have it. It's not ready yet. So this is the one thing that basically you still do really need the terminal for, because the notebook is still missing that particular. We can't grab the standard input from the notebook, from the sub-process yet. Okay? Yes? Yes. Yeah. So there is another bit of capability that I already hinted at with the %pylab. I think we're going to be actually just perfect on time. There's another bit of capability that the pylab thing hinted at, because pylab, when I called pylab, I said pylab inline. That forced matplotlib to send me the figures as PNGs or SVGs to show inline. But I actually could have said pylab with a GUI, flag to say, give me load matplotlib, but give me Qt windows, or give me WX windows, depending on what toolkit I have installed, because matplotlib can actually pop up interactive plotting windows. And that control for interactive GUIs actually is not specific to matplotlib. It's actually pervasive in IPython. So we actually have a magical %GUI that lets you hook the event loop of IPython with the event loop of a specific GUI toolkit. You can switch between them. Switching between GUI toolkits at runtime is kind of a mess, but you can at least do one of them. So I want to show you here, this is a very simple example of a little teeny bit of Qt code. Once I say %GUI, I can say GUI WX or GUI Qt or GUI TK or GUI Piglet. We have like 6 of them. If you do %GUI question mark, you'll see all of the available ones. Then if I have a little bit of Qt code here, and then I actually build, this is a teeny example taken from like a mini tutorial, right? Never mind what the code does, it just pops up a window with a button. But if I run this code, in here we have a little bit of library support in IPython to hook the 2 event loops. And when I run this, I have here a little Qt window, but I can still run code in my IPython window, okay? Which means this is running the Qt code, and the event loop for Qt is active, and I can click on this button and close it, but my interactive terminal remains live, which normally doesn't work in plain Python. And you can do that from the notebook, or you can do it from the terminal, and you can do that with Qt, WX, TK, Piglet, Glut, and I think that's about it, okay? So this is important, and this goes to your question, which is now, how do you embed IPython? So now we're beginning to couple this notion of a kernel with event loops. And first I'm going to show you how to embed it in a terminal, and then we'll see how to embed it in a GUI application, the full kernel. So if you simply want to embed plain Python in a process, this is all you have to do. From IPython, import embed. And whenever you call the embed function, and you can give it a header argument so it prints a little statement, it will open up an IPython shell. So this is a file that I called simple embed. And if I go to my terminal, let me get out of here, and I run just Python simple embed.py, look at what happens. First time pops up. That's exactly what I had said. Embed here and print first time. And variables A and B were defined as 10 and 20. A is 10, B is 20. When I quit this, it goes back into the code, and then the next time an embed call pops up again, it'll come up again. And so now C and D have been defined. It said embed header second time. Now I have B, I have C and D. And when I quit, the code finishes. So the point is, whenever, if you ever deep inside of a piece of code you would like to do a little bit of rich interactive introspection, all you have to do is from IPython import embed and call embed right there. Because that'll open up an IPython right at that point in the code with access to all the local namespace. You can do whatever you want, and then you can get out. So it's a very handy way of adding pretty deep introspective capabilities into an existing code at any point in the execution of the code. All it takes is one call. From IPython import embed. That's it. And then finally, oh yes, here. The last point that I'm going to cover, and then we'll switch to Brian, is the embedding of the full kernel. This was just embedding the IPython interactive shell in a shell application. But what if you're running a process that doesn't have a terminal attached to it and you would like to control it with IPython? You can do that too. So in the there's a directory called kernel embedding in the examples that I gave you, and there's a little WX application example. So if I run this WX application, whoops. Okay, give me just a second. I know what happened. The API changed a little bit. I'm sorry about this, which means, okay. So if I run, sorry, I'll fix the API, or one call in the API changed, and I had the new version. So because we're running tight on time, I'm going to switch to this one. So this is a little WX application that has very simple code. It has some variables. There's a namespace variable in there. And what I did was I added a little bit of code, this kapp code, which embeds a kernel, an IPython kernel. All I have to do is say, grab me an IPython kernel instance and initialize it with GUI support. And I initialized it. And this, where is my? And this thing right here is its own app, but it has an IPython kernel running. And I actually added a button to open a Qt console so that I could actually control this kernel. So it has a single piece of data in it, a counter. I can increment that counter. I can print my namespace. I can increment it further. I can print the namespace. Now it's 4. I can say app counter, it's 4. I can set it to 100. Now if I increment it again, and I print it again, now it's 102. So the point is I have a GUI application, but that GUI application is running an IPython kernel on the inside. And that kernel has one of these Qt consoles attached. As I told you, if I ask for connect info, it will tell me what the port information is. So just to show you that this really is this app running from a real kernel, if I go here, if I go to this console, I get a prompt numbered at 4. And the app counter is exactly 102, which is what I was connecting to from what I was seeing from here. So this shows me how I can start with a very tiny snippet of code. And this is the entire example is 2 files. This one file that creates the kernel and configures it to have the WX event loop integration, because this is a WX app, right? And then the WX code itself, which is just copied from a WX tutorial, and I simply wired a couple of WX buttons to talk to the namespace of this kernel. So this is something that you could crib if you need to basically add a kernel into any process, and now this kernel is listening on the ports, and you can connect to it from any of the clients. So just like I connected to, I added the button to explicitly spin up a console, but getting the connection data, you can connect to it from a terminal, from a notebook, from another process. So it's a very useful way of adding basically full interactive control to any complex process for which you may not have added GUI elements, or where you may not have sort of developed yet, you may not have decided yet what are all the other controls that you want to add. Well, this gives you real code. You can just connect into it and manipulate it, okay? So this kind of covers the core of the architecture, and I'm exactly at 10:15, which is where I was trying to hit. So I'm going to stop here. Thank you for your attention. They asked us to take one long 20-minute break in the middle of the tutorial. We're going to break with protocol, and instead we're going to take 2 shorter 10-minute breaks, because there's 3 of us. So it just makes a lot more sense to break in between speakers while we change mics and all that. So we're going to take a short 8 to 10-minute break now.
My name is Brian Granger. I'm one of the core IPython developers. Most of my recent work has been on the IPython notebook, but as most of the IPython developers have, I've worked on a lot of the code base. So we want to take you into more depth about the actual IPython notebook, and that's what this sort of middle section is going to cover. The last section will cover, that Min is going to do, will cover the configuration of IPython, and then IPython's parallel computing tools. And you can follow along in the IPython in-depth repo, the notebooks that we have there. I'll be starting with the Notebook Basics notebook. If you want to open up that, there's not really a lot of code to run, but you can still read along. And so I want to start by covering some of the main concepts and the UI of the notebook. And the first thing that you need to understand is the idea of the project directory, or the notebook directory as we call it. So you've probably noticed by now, when you CD'd into a directory that had these tutorial notebooks and typed IPython space notebook, that the notebook dashboard showed only the notebooks that are in that current working directory. And that directory is what we call the notebook directory. There's nothing special about a notebook directory other than the fact that it contains notebook files. And this is the other important abstraction, and that is that notebooks are just standard files on your file system. We do not store these in some fancy database that's hidden from you. They're just files. And that was a really important part of the design of the IPython notebook, mainly because a lot of people are, or I would say should be, saving all of their work in version control systems. And files are the main abstraction for version control systems, and so we wanted notebooks to be friendly towards that. Now you may be wondering, well, what if I want to change directories and look at notebooks in a different directory? Well, right now, unfortunately, you have to start a separate server in that other directory. We realize that is a pain, and we are actually in the process of working on that. Hopefully, not too long, the dashboard will actually have the ability to change directories and view notebooks throughout the file system. The next thing about notebook files, notebook files are, like I said, they're just files. They have an IPyNB extension, and notebooks are just JSON data. JSON stands for JavaScript Object Notation. It's a serialization format, basically, that JavaScript knows about, but these days, just about every language you can imagine has JSON libraries. And so to show you what this looks like, here's a little bit of Python code. In the IPython package, we have a sub-package called NBFormat that's responsible for reading and writing these notebook files. These notebook files are versioned, and I don't mean versioned in the sense of like version control. What I mean is that the notebook format itself has versions, and this allows us to update the notebook format in a sane way. Right now, we're on the V3 version of the notebook format. At this point, I don't think anyone should have the V2 format notebooks. Those haven't been used in the wild for quite a long time now, so I don't think you should have to worry about that. If you try to open an older format notebook on a newer version of IPython, when you open it, we will tell you it was an older notebook, and we upconvert it automatically to the new format. So that's how we handle that. So let's just actually read the JSON of this current notebook that I'm working with. And our current notebook format has a concept of worksheets. That is actually going to go away, so sort of ignore this middle section here. But once you read the JSON into Python, it's just a Python dictionary, and you can see what our notebook files look like. There's different cell types. I'll talk more about that. You can see, yeah, it's a very simple format. And we really wanted to stay simple with this. We actually went through probably 4 different iterations of the notebook format before we settled on using JSON. We had, I think, 2 different versions that used XML, 1 version that used a database, and we are extremely happy that we went with JSON. It's a perfect tool for this type of purpose. So these notebook files contain everything. So when you see a notebook open in your web browser and you're seeing code, text, images, equations, The notebook document has all of that. For the images, for example, we base 64 encode those and save those in the JSON data. So they're, yeah. These notebook files are maybe a bit of a stretch. We like to think that they're version control friendly. They're not a binary format, and why this is relevant is this allows you to post your notebooks on GitHub. A lot of people are doing that. We encourage you to do that. Share with us, with the community, the things you're doing with the IPython notebook. And the main thing to know about sharing notebooks at this point is that we have nbviewer.ipython.org. You can paste GitHub URLs, actually any URL on the internet, and NBViewer will render that JSON file so that anyone can see it. And these are not executable notebooks on NBViewer. It's just a static HTML rendering. So if I try to click here and run that code, I can't, but I can actually download that notebook. And you can see actually in the download, or the URL down at the bottom, that it's actually on GitHub, this particular notebook is. So IPython notebooks can also be exported to .py files, and this is obviously a lossy process. You can't stuff markdown text and images and equations into .py files. You can think about doing all sorts of crazy things like trying to put that content into comment blocks in Python. At some point, though, we feel like that's just not what the .py file format is for. This is the main purpose of this is for if you have a notebook, but that you also want to be able to import code from that. That's one purpose. The other thing is that the conversion process does go the other way. So you can actually create a .py file, add a small amount of markup in comments, and automatically convert that to an IPython notebook. Yes, that's a very good point. So for example, if I were to export this current notebook to a .py file with the name of notebook space basics, Python is not able to import modules with names like that. So you'll have to name your notebooks with import-friendly names. So if you find yourself often wanting to have these .py files around, you can start the notebook server with the -- script option, and this will automatically create those .py files each time you save the notebook. And so I actually want to have you start to play with this and get used to the workflow of working with notebooks. Show you a few things first. So in the file menu here, there's a download as. You can actually download the IPython, the JSON of that. You can also download the .py file. So let's actually look at what that looks like. So there's not a lot of code in this notebook, but you can sort of see what this looks like. So the basic markup that we have is sort of like HTML type tags that are put in Python comments. So we do preserve heading cells, you can see, and the level of those heading cells. We preserve markdown cells, so it has the text. And then we obviously preserve code cells, and code cells are top level uncommented, so you can actually run that Python code. And so that's what I mean by this .py file format. And again, you can start with a .py file, if you start outside the notebook, and if you just want to import that into a notebook, if you just go through and add that line right there between each point where you want to separate the different code cells, you can import that and you will have an actual IPython notebook that works. Yes?
Does it put back the headings and the various things we commented there?
Yes. Yeah, no, I mean, it's like I said, it's a lossy process, not entirely lossy. So the heading cells get imported, the markdown cells get imported. The main place where it's lossy is in images that are embedded in the notebook, and then also notebooks and cells have metadata associated with them, and that metadata is also lost. So, yeah, you know, we try to preserve some of it, but obviously can't do all of that. So that is exporting through the file menu. Obviously, if you're running the notebook server on a local system, you have access to the file system. You can just go right in and work with these files. So you can always, quote, import and export by simply copying notebooks in and out of that notebook directory. But if you're running a notebook server and don't have access to the local file system, this is useful for exporting. For importing, the way that works is from the notebook dashboard. You can click here and it pulls up the file dialog and it allows you to pick a notebook that you'd like to import. So for example, here I have a directory of notebooks. This is our example directories, and I could just pick a notebook here. You can actually rename it like that and import that, and then you can open that notebook like that. So at this point, I would like you to do an exercise, and well, we'll see how this works. I was testing it out, and the internet has been working okay. But what I'd like you to do is find a notebook on nbviewer.ipython.org, download it onto your local system, and then from the downloads directory, go into the IPython notebook dashboard for the current notebook server that you have running. Click here and import that notebook into your current notebook server. I want to spend some time now talking about the user interface of the notebook. And by now you've seen the notebook in action for an hour and a half. And so you've realized that there's this main area here down at the bottom. That's the notebook area. And then if you start to click on cells, you'll see this thin gray border that will select a single cell. And if you then use the up and down arrow keys, you can adjust what cell is selected. And the current model is that a single cell is selected at a time. The selection model may change in the future if we implement multiple select, something like that. And the cells are really the fundamental unit. And so when you think about what is a notebook, you should think a notebook is a linear ordered sequence of cells. And there are different cell types. We'll get into that here shortly. There's also this heading area here. If you go to the View menu, you can toggle that header if you'd like more space to work. Then we have the main menu. The File menu has obviously New. It has Open. Open will take you back to the dashboard. There's Make a Copy, which will just make a copy of an existing notebook in place. Rename, Save. The way that most people save is with keyboard shortcuts. On Apple, Command S will save your notebook, so let's do that. And actually, if you look, another thing about the UI, right here, there's actually a notification widget. It's hidden right now. When you run code, save the notebook, load the notebook, there'll be messages here. So I'm going to just press Apple S, and you can see that it says notebook saved. Just a warning, right now, the IPython notebook does not have any sort of autosave. We are working on this. This is high on our list for our next release. What this means is that you can lose notebooks. One way that I would say is probably my favorite way to lose work that I've done is to not save it here, close my laptop, and then I get busy. I come back 2 days later, and I come back and I see this, and I start closing terminal windows, right? And that will kill the server, and you will not be able to save the notebook. If Min, and there's a couple other people that use this as well, actually have an extension to the IPython notebook that implements sort of a temporary version of autosave. If you're interested, did I lose audio? No, okay. If you're interested in that, ask one of us or Min and we can point you to that. But again, that is something we're working on, but please be careful. The other thing, another bug with sort of notebook management, if you rename a notebook and use a name that's already taken by another notebook in that directory, it will overwrite the other notebook without warning, right? So that's another fantastic way to lose work if you're looking for those things. Again, we realize that's a bug and we are working on that. So let's see, the edit menu, I'll talk about the edit menu more when we actually get into working with cells. There's different cell actions you can do here. You can also toggle the toolbar. Insert, the two insert actions are insert cell above, insert cell below. Again, we'll do some exercises with those. There's a kernel menu, we'll talk about that, and then there's help that we'll get into. Other things, the other place to create a new notebook is here from the dashboard. You can also notice that once you start to run notebooks in the dashboard, the delete button changes to a shutdown button. And so, for example, the progress bar notebook is running and I can shut it down. And one thing that's important about our model with the notebook and the kernel is that for each notebook, there's a one-to-one mapping to a kernel, right? And so when you have multiple notebooks in a directory like this, when you have multiple of those notebooks open, there are multiple IPython kernels running in the background, running the code from those notebooks. And when you open a notebook, we start a kernel. If there's a kernel that's already running for that notebook, we reuse that kernel. So for example, I'm just going to close this notebook, Notebook Basics. When I close it, go back to the dashboard, you'll notice it says it's still running. And actually, I can go back to Notebook Basics, and if I go down here, I can rerun this line of this code right here, and the NB object is still defined because the kernel never went away, right? So the toolbar. This is, again, the toolbar. This is a save button. We've got cut cell, copy cell, paste cell. This is move cell up, move cell down. So I can click on a cell, move it down, move it up. I can select on a cell. These two buttons here, insert a cell above and below. The default cell type is always a code cell, as you can see there. This runs the cell, and this interrupts. So this button here is equivalent to kernel interrupt. This right here selects the heading type of the currently selected cell. So let's see here. Yeah.
Curious, when you move the cells up and down, how does that interplay with underscore, number?
So this is a really important point. There are two concepts of reality here. There's the kernel, and then there's the notebook document. The state of the kernel and the state of the notebook document are completely independent. We were very deliberate about this. The kernel knows absolutely nothing about notebooks. And I mean, to be honest, we couldn't have developed the different front ends, the terminal, the Qt console, the notebook, if the kernel knew about front end logic. Prompt numbers are information that really lie on the kernel. Like the kernel has an order of code that it's executed. When code comes back, so if I just run some simple code here in the notebook, notice it starts out with no prompt number. The reason there's no prompt number is that it does not know what the state of the kernel is, right? The kernel, you could have in the meantime run code from the Qt console and incremented the kernel's prompt number. And so the front end can't guess when we run the code. When the results of that code come back, we fill in the prompt number that reflects the current kernel state, but that is completely independent of where that cell sits in the notebook. So I can start to move that around and it's completely decoupled. Does that clarify this? Yeah, that's a really good question though. All right, so what I want to talk about now is more about cells and cell types and cell actions. And for that, I want to just create a new notebook. And why don't you do the same? Let's actually type some code together, move things around. So if you're like me, when you start working on a project, the first thing you probably do is start coding. And so let's fire up Matplotlib and Pylab inline. And let's say we've made a plot here. Notice as we work, when you run the last cell, we automatically create a new code cell below that. But if you go up to this cell, and for example, click Insert Cell above here, we get a new cell above this. And at this point, well, let's work a little bit more. So maybe at this point I realize, gosh, I want to start to describe what I have. And for that, you would use a markdown cell, which is basically a text cell. So there's two ways you can get a markdown cell. First, you can just go here and select markdown. And now I can type markdown text. Markdown is a markup language, sort of similar to restructured text, although not that similar. You may wonder, why on earth did we pick markdown and not restructured text? It turns out that restructured text is horrible for things like this. The main issue is that restructured text, in a context like this, needs to render entire documents at once. And with Markdown, we're able to render individual cells one at a time. Using Markdown would mean we would have to send the entire notebook document back to the server to be rendered at once and then come back each time you edited one cell. And we're actually pretty happy with the choice to go with Markdown. So here's Markdown text. To render the Markdown text, it is Shift-Enter. So you can type Shift-Enter and you see the actual Markdown text that's rendered there. And this is just a normal cell. So for example, you can move that cell around, go up, go down. You can make a copy, click copy cell, and do we have a bug? Let's see. So paste cell below. So that works. This may have a, no, that's a bug. And one thing to emphasize, the edit menu here has cell level actions. And cell level actions are very different from sort of text editing that you would do within a cell. For example, if I wanted to edit this Markdown cell, you can either double click or you can simply press Enter to edit that. if I'm in a cell like this, I can click on some text and then do the standard Command C for copy and Command V for paste. That's text level operations. When we say cut, copy, and paste of a cell, we're talking about the entire cell itself, not the text within the cell. For the most part, the standard text editing keyboard shortcuts do work within cells. So that's markdown cells. Let's go up here, and we can delete a cell. The other cell type is a heading cell. So maybe we want to add a heading to this notebook. So we can click New Cell Above, go here to heading 1, and type my notebook. And you can see that that is rendered as a heading cell. Well, I'll talk more about how markdown cells and heading cells interplay shortly. So, any questions about sort of basic cell operations? Other actions that you can do on cells, there's the ability to split cells. So this will take your current cursor position and split a cell into 2 cells. So if you have pasted a huge block of Python code into one cell and want to split it into multiple cells, there is merge cell above and merge cell below. This will merge with a cell that's above the currently selected cell or below. You can also toggle output. We'll talk more about that. Probably the easiest way to do this is if you have a cell that has output, you'll notice if you hover over the output prompt here and you double click it, that output will be hidden. And it's replaced by this bar. You can click it again to see that output again. There's also the option here under all output to collapse all output, which is basically toggle, and then also clear all output in a notebook. So, yeah.
Really, there's keyboard shortcuts for operating itself. You shouldn't have to go up to create a new cell, right?
Yeah. Absolutely, there's keyboard shortcuts. Of course. Yes, so we have keyboard shortcuts. Under Help, if you go to Keyboard Shortcuts, you can see all of our keyboard shortcuts. For the most part, it is Control-M and then a modifier key after that, other than Shift-Enter and Control-Enter. I'll talk about Control-Enter in a second. And I guess the only other one that is treated special is Save. So you can do Control-M-S for save, or Control-S or Command-S work as well. Ones that I tend to use a lot is for inserting cells above and below. So if you do Control-M and then press A, you get a cell above this. Control-M-B for below, you get a new cell below. We get a lot of questions about if it's possible to customize the keyboard shortcuts. The answer is that not easily. It turns out that browsers and operating systems are not a clean slate from the keyboard shortcut perspective. In fact, most good keyboard shortcuts are already taken by the browsers and operating systems themselves. That is why we have this sort of, not wonderful Control-M and then a modifier key. For our code cells, we actually use CodeMirror. CodeMirror has Vim and Emacs editing modes. We don't have those enabled, but those are something that's on our roadmap for development for the next release. I don't think those key bindings are wonderful. I think they're the type of thing that will hopefully appease the hardcore Emacs and Vim users. So let's see here. I think I'm going to skip this exercise. There's a lot of content to cover still. So next, I want to talk a little bit about running code. So as you've seen before, if you hit Shift-Enter, you run code in the normal fashion. But there's some times where you almost want to switch into more like a terminal mode where you're not going to always create new cells. And that's what Control-Enter is for. So for example, if I hit Control-Enter, it runs that. It does not insert a new code cell, and it actually selects the input from the previous command. And so you can just start typing. So you could do cd ... Control-Enter, ls, Control-Enter. It gives you like a mini terminal type feel. We've gone back and forth about whether or not it should actually, Control-Enter should delete the previous input or not. We feel like selecting it is sort of a good compromise. Another thing to notice is that I just did a CD in the notebook, right? But if I go back to the dashboard, it still shows all the notebooks in the original notebook directory. What you may realize from this is that the current working directory of the kernel is independent of the current working directory of the notebook server, but they start out as being the same, right? And so once you start a kernel, you can actually walk that kernel around the file system and look at files, do whatever you want with the file system, but the notebook server will remain fixed in that directory. Part of what's a little challenging when you start to think of the notebook server itself and the dashboard being able to navigate to different directories, all of a sudden there's a lot to keep track of, right? And that's complexity that we want to mitigate. We don't know how we're going to do that. So managing the IPython kernel. So for example, I can start some code that runs. You'll see kernel busy here. I can click the stop button and it will actually send the signal to the kernel that causes keyboard interrupt. So that works. Here is some Python code that will actually segfault the kernel. So this uses, loads up a C library in C types and calls it incorrectly and segfaults it. And let's run that. This won't work on Windows. The kernel is busy, and you'll see that the IPython notebook server detects that the kernel has died and gives you the option of restarting the kernel. And so those are sort of the two things that we can manage. Another thing that we can try out is we can define a simple variable here. And something that often happens as you write Python code is that you start importing modules into your kernel. And you may be developing those modules and they may have extension code, and you basically need to wipe out the kernel and start over again. And we make that really easy. You can go up to kernel, restart, you restart it, and if I go below and try to print A, you find out that A is cleared. The entire kernel process gets shut down, restarted, everything gets hooked up again. Yes?
The line number or the int, like if you scroll up to the segfault code, you still have to put the asterisk.
That means that cell is running. We just didn't do a good job of clearing that. Yeah. So Fernando mentioned a little bit that you can paste external code snippets that have Python prompts or IPython prompts into notebook cells, and those will run. The other thing I want to show you is the load magic. Load allows you to take Python code from a file or URL, and it will inject it into the contents of a yet to be created cell right after that. And so let's actually look at this. Again, given how time is going, I think I'm just going to show you how this works. So here I'm going to load some code that lives on disk. So I run that, and all it does is inject the contents of load.py into the next cell. And so actually, if I go over here, let's see if I have this. Yeah. So for example, here's those files. Load.py just has that code. So you can actually store Python code on the file system and load it in that way. But notice the code that I'm about to run also uses the load magic, but it pulls an example directly from the matplotlib gallery. So let's just run this. It starts up PyLab and then injects that matplotlib example into the following cell, and then I can run that and the example actually shows. So again, this is a really nice way for exploring code. You can go to the matplotlib gallery, grab code quickly, and run it on your local system. There's also a run all. So run all will run all of the cells in a notebook. Okay, so I think that's all I want to say about running code. Let's see, I want to make sure. So I'm going to spend a few minutes talking a little bit more about Markdown and then equations in Markdown and in the notebook. And then we're going to spend about the last 15 minutes going over our display system for the notebook. And I think that's some of the most fun parts of the notebook. So here's a notebook that has some examples from Markdown. If you're interested in the syntax, if you just Google for Markdown syntax, you'll find the documentation for the syntax. Notice here, this right here is a heading cell, this first cell. Here is a Markdown cell. Again, to edit a Markdown cell, you can press return or double click. And one thing that's important to know is that Markdown is a superset of HTML. What that means is that you can just type HTML into any Markdown cells and it will do what you expect. Right now, you can actually even type scripts into Markdown cells. That feature will likely go away because of some security issues. You can see just some examples of syntax. So there's italic and bold. There's lists. So you can see it's the usual type of Markdown syntax for lists. There's horizontal rules, block quotes. The link syntax for Markdown, I really like it. I think this is an area where restructured text really just made horrible decisions about what that syntax looks like. You can also just put raw URLs and Markdown will handle those as well. Now, Markdown has its own concept of headings. And so let's look at this Markdown cell. And you can see there's a single pound, a double pound, triple pound for the different Markdown heading levels. And when I render that, they look like heading levels. And you may wonder, well, what's the difference between an actual heading cell, which is right here, and headings in Markdown cells? And the primary difference is that heading cells tell us about the structure of a document. And part of what we're doing currently with the IPython notebook is we're developing the machinery to export IPython notebooks to different formats, to HTML, to LaTeX, to PDF, to reveal.js slideshows. That conversion machinery knows about heading cells, and it is able to map heading cells onto the appropriate structures in the output formats. The headings that appear within Markdown cells, that conversion machinery is completely ignorant of them. What this means is that most of the time you want to use heading cells and not the heading markup in your Markdown cells. Our conversion machinery does use pandoc to convert Markdown to different formats. And so it's not like that those will be completely ignored. It just won't be properly reflected in the overall structure of the document that's exported. Markdown cells can embed static code. So you can see that this code right here is not code I can run. If I press return to edit that, you can see it's just indented Python code. And we actually have a syntax highlighter built into our Markdown cells as well. And you can see if the default is indenting 4 spaces. You can also put code within Markdown lists by indenting the code by 8 spaces, which is really nice. By default, Markdown does not understand equations in any way, shape, or form. We have added to the Markdown syntax to allow for that. And so, for example, here is a Markdown cell. And you can see I'm using dollar marks and putting inline LaTeX code. Our LaTeX code is rendered by MathJax, which is an in-browser JavaScript implementation of the equation rendering part of LaTeX. It's not a full LaTeX implementation. And then the double dollar marks give you the LaTeX display mode math that's non-inline. And MathJax is an absolutely fantastic library, and it does a really good job of rendering. As I said, Markdown is just HTML. So here is an HTML table in a Markdown cell, and well, it's an HTML table. We have style sheets that apply to Markdown. And we tried to have sort of reasonable defaults. But because Markdown is just HTML, you can actually type CSS style sheets into Markdown cells and style your notebook however you want. And so you probably saw one of the notebooks, the Bayesian analysis notebook Fernando brought up. It was styled very differently. It had different fonts. It had larger margins on the left and right side, and all that is done by simply typing CSS into a style tags in a Markdown cell. It applies to the entire notebook. Those style tags are injected into the DOM using jQuery, and so they're handled as such, and it's global. So you can also refer to local files from Markdown cells, and the syntax is files / any subdirectory and then the file name. And this is important, it's not /files, it's just files. And so, for example, in our figs subdirectory in this notebook directory, we have the Python logo. If we click on this Markdown, you can see I can actually just put in an HTML image tag, and it will find that file on your local file system. And this works not just with files like that, but here's an actual video that's on the local file system that you can load. So from a security standpoint, we are serving files from your computer, and if you want to run a notebook server on a public system, it's probably not a good idea to start that notebook server at a high level like / on your file system, because these file URL will give the notebook access to every file on your file system. So, you know, there's things to be aware of there. So before we jump into the display architecture, just wanted to show you a few examples of other LaTeX. Mainly, I think, just wanted to show you a longer example. So here's an example. You don't necessarily have to use, especially for the display mode math, the double dollar mark. You can use other ways of demarking LaTeX math. And there is a bug on the version of IPython that you are probably using, 0.13 series. And normally when you type LaTeX, the new line is just double /, but because of a bug in our parsing of Markdown and LaTeX, in your version you have to do triple /. That is fixed in IPython master, so you could just do the double /. So if we look at the actual code here, the triple backticks here are marked down for pre-formatted code or pre-formatted text. This is the actual markdown that gets run, and you can see it gets displayed like that. You can, as I said, use double dollar marks, and I think that's all I want to say about LaTeX math. So I would say part of our goal with IPython is to make coding fun for you. We code because we love it, and we hope that we can sort of spread that way of thinking about coding. And I think one of the main ways that IPython is fun for people is through this display architecture that I'm going to cover now. The basic idea is that in Python, objects can declare their textual representation. This is done using the repr method, and any object can define a repr method and return a string from the repr method, and that string will then get displayed when you're running Python code. So for example, if I just do a equals 10, and then I do a, the way it gets 20 out of that Python object is it calls the repr method, right? What we've done with IPython is extended the repr idea to other data types. And currently, we allow Python objects to declare HTML, JSON, PNG, JPEG, SVG, LaTeX, and JavaScript representations. So you can define special methods, just like repr. They have different names, and on any Python object. And once you do that, those objects will automatically be able to display those representations in the IPython notebook. And actually, the Qt console handles a lot of these as well. Now, you probably are realizing, well, how do you control which representation gets generated, which representation gets displayed? Obviously, Python's print statement does not know about this at all. And so we wrote a function called display. Display, the basic algorithm of display is that it tries to find the richest representation to display and use that representation. When the Python objects are run through the representation machinery, we actually construct all representations in the kernel. And the reason we do this is that different front ends, the console or the notebook or the Qt console, may or may not be able to display the different formats, right? The terminal is not going to know what to do with an HTML representation, but the notebook would be able to do that. All of those representations are brought back to the front end, to the notebook. The notebook then makes a decision about which to display, and in fact, all of those representations are saved in the notebook format. The reason we do that is that when you convert that notebook to different output formats, you may want to, again, display different representations. So there's a basic display function, and then we also have a set of functions that can display a particular representation. So let's start to look at this. So we have created an image class. The image class simply has defined the special method that makes it able to display and render images. So here is an image that we're pulling from a file name. We can create that object. And if we just return that as a Python expression, we see that image rendered in the notebook. We can also cause that to happen using display. Now, why would you use display versus just returning it? Well, for example, let's say you have a loop, and at each step of the loop, it's computing some image, and you want to display that image while it does the computation. In that context, you would not be able to use this syntax here. This only works for basically the final object that's returned. For something in a loop, you would need to call display at each iteration of the loop. All of this is asynchronous. So if you have a loop that takes maybe 5 minutes each iteration of the loop and it generates an image, if you call display each time the loop finishes, you're going to see that image immediately. It will go back to computing and you'll see the images updated in real time. You can also...
The mental model that you should probably keep in mind is display is your print equivalent. So wherever you would think in a terminal code, you would put a print statement. If you want to show a more complex object, use display. So it's exactly the mental equivalent of print instead of getting the wrapper out, but for these richer wrappers that Brian is explaining. So display maps the print in your mind.
Yeah, great point. So you can also pull an image from a URL. So here we can run this, and we can grab that. Now, the important thing here is that, remember what I said, in general, all of your data is included in the notebook document itself. When you pull an image from a URL, that is an exception. By default, this image right here is not included in the notebook format. Images that are pulled from the file system are included in the notebook. You can force the image to be embedded in the notebook document by passing embed equals true. Right? So if you have a notebook that you want to share with someone else and you want to make sure that that image will appear by default when they open the notebook, if you're pulling images from a URL, do embed equals true. We also have an SVG object. The SVG object works similar to the image object, but it has the special method required to let IPython know that it has an SVG representation. So here we can run this and see an SVG repr of the Python logo. We're running short enough on time. I'm not going to have you work exercises. I could actually probably talk for another half hour about this. We have a YouTube object, and you can just pull the YouTube ID off a video, press return, and you can see, so this is a talk Fernando gave a while back on IPython. And I hope what you're starting to see is that this is not just about code and a little bit of markdown text. The notebook is a document format that allows you to incorporate a wide variety of content and sort of tell a story with that content. So we've already seen how you can put HTML in markdown cells, but what if you have Python objects that have reasonable HTML representations? Well, you can actually convert Python objects to HTML. So here's, we have an HTML class that knows how to do that already. Here's some HTML code in a string. And when we return this object, we actually see the HTML header rendered there. As I mentioned, we also have JavaScript representation. So there's a JavaScript display object. I'm not going to go into much detail here other than to say this JavaScript object, when it's returned, comes back to the browser with the JavaScript to run. The notebook detects that and actually runs that JavaScript. Here I'm loading the D3 visualization library. Here I'm actually going to run some HTML that styles some things. And then this is just one of the D3 examples off the D3 website wrapped in a JavaScript object. And you can see you get a really nice D3 output in your notebook. Just a warning, because of some of the security implications of the way JavaScript code is run in the notebook, we are going to make some changes to what it looks like to run JavaScript code, the JavaScript representations. It will always be possible to run JavaScript code, but again, things may change in terms of what that exactly looks like. So Pandas is a very nice library for doing data analysis. The primary object in Pandas is a data frame, which is basically a table of data. And Pandas data frame objects have the right special method to declare the HTML representation. So here we can import Pandas. You have to set this option to tell it enable these HTML representations. Here's some stock data. We read that. So I'm just using the file magic to save it to a CSV file. We use Pandas to read that, and then the representation of that data frame is a nice HTML formatted table. SymPy is a symbolics mathematics library. SymPy deals with mathematical expressions. And SymPy has an extension that I just enabled here that teaches SymPy objects what their LaTeX representation should be in the notebook. And so we can create some SymPy objects, and when I return those, you can see that those come back as LaTeX. The notebook picks that up, and they get rendered using MathJax. And so it makes it really nice to work with mathematical expressions. You can embed other websites, right? I mean, iframe is just a way of including other websites or other pages in existing pages. So for example here, the internet, oh there we go. You can just embed a Wikipedia page in the output of a cell. We have math and LaTeX objects that you can pass LaTeX to. The difference between math and LaTeX, math does not require dollar signs to denote the math. LaTeX, you have to actually put in the double dollar signs or equation array or something like that. So in the last few minutes that I have, I want to talk briefly about how you can start to add this display logic to your own Python classes. And for that, it's the custom display logic notebook. And again, we've covered a lot of the intro material of this, and I want to focus on this section here. So first is, what are the names of these methods that you need to implement? So the general pattern is underscore, single underscore, repr underscore, the name of the output type, and then a trailing underscore. So repr HTML, JSON, JPEG, PNG, SVG, LaTeX. I didn't list it. JavaScript is also an output format. And here's what those methods need to return. Most of them need to return Python strings that contain the appropriate raw data for that type. The only difference is JPEG and PNG need to return the raw JPEG or PNG data. So here's a little example. Let's say we want to write a Circle Python class, and we want to teach our Circle Python class about different representations, right? And for the HTML representation, we're going to use this. For SVG, we're going to use this snippet, and for LaTeX, we're going to use this. So here is the Circle class that I've written. And you can see I just need to define these special methods. Again, under, repr, under the format, and then a final under. And then I just need to return the relevant output for that particular type. So this here is valid HTML. This is valid SVG. For the LaTeX, notice I need to wrap it in the $sign. And then for JavaScript, I can just put JavaScript code. So let's run that. And I don't need two of those. I create a Circle instance, and let's actually just return the Circle. And so notice, remember what I said, the default display logic will try to find the richest representation. For us, the richest representation is JavaScript. And so that's the representation we get, but then if we go here, we can display the HTML, the SVG, the LaTeX, and obviously the JavaScript again. So it's really not difficult to add this display logic to your classes. And so go home, add this. People are slowly finding out about this and doing really, really cool things. Matt Davis is giving a talk at PyCon during the normal conference session. He's going to be talking briefly about a library he's created called IPython blocks. And it's a library for generating sort of visually interesting HTML tables that are useful for teaching people things about programming. And so definitely check that out to see the type of things that people are doing with this. Now you may wonder, well, what if I use a library from someone else? So I don't control the source code. And it doesn't have all these special methods, but I want to teach IPython about how it could build an HTML representation of that object. You can do that. It's a little bit more involved. You have to access the IPython formatter logic. So we have a list of formatters that handle these different things. Here's the actual PNG formatter, and then there is a for-type method, and I'll show you how that works. So here I'm going to teach our Circle class about a PNG representation. I need to define a function or a callable that takes the objects I want to display and returns the data for that particular format. And so I register that for type Circle, PNG Circle, and telling the PNG formatter about that. And then when there's something really weird about this notebook that I don't understand. Extra credit if you can figure out what's going on. So I don't, there's something, yes, I redid this, and I have no idea why it didn't work the first time. Yeah. And so you can see a matplotlib generated PNG representation of this circle. Another thing that's on the horizon, we are currently working, and work will begin in the latter half of this year, to expand this display logic to enable richer, what we're calling JavaScript widgets, where you can have JavaScript running in the output area of a cell and talking bidirectionally to Python code on the other side. And that will sort of open the door to a wider range of visualizations, interesting sort of widgets that you can sort of couple Python code into the browser. And so we're currently working on that. So I think I'm going to stop there. We need to take let's take about a 5-6 minute break, and then Min will come up and finish the last section.
2 topics. The first one is going to be configuring and customizing IPython a little bit, and extending IPython with custom behavior that you want to do. And then the last topic, we'll be talking about some of IPython's parallel computing machinery, which will be mostly kind of a glossy, just showing stuff on the surface, because it would take me more than a couple of hours to kind of get into the real detail of that. But to start out with configuring IPython, there's lots of stuff you can configure with IPython, and I'm going to kind of show you ways to get into, to kind of find out what you can configure. So to start out, if you want to check what options IPython has, you can just do IPython-H. So I'm just, in the notebook, you can type this in the terminal if you want. I'm just typing it in the notebook with the prefix bang, which is equivalent to if you were typing it at the terminal. So IPython-H gives me lots of output about various things you can do with IPython. IPython has subcommands for anybody familiar with Git, so that there are different things you can do. IPython is kind of the top level entry point, and then you can launch these other subcommands to do things like start the notebook server or start the Qt console, or configure IPython with profiles. And then there are all these flags you can use to customize IPython. For instance, if you want to start an IPython terminal with Pylab hooked up, or customize some common configuration options with colors or with debugging and things like that, or the debugger, or what's that mean? And so we can literally everything configurable in IPython is actually configurable from the command line. So I just did IPython-H, which gives you a short list, but if you do IPython-help all, it will actually show you everything you can configure in IPython. And this is an automatically generated list based on the configurable attributes of all the classes in IPython. And this shows you all the classes you can configure and all the different things you can do. So for a quick example, if you want to find something that you want to change about IPython's default behavior, a useful trick that I use a lot is doing piping help all through grep. So grep is just a simple pattern search. So one of the most common requests we get on IRC and things like that is if I'm in a terminal IPython and then I exit, there's a confirmation message. Do you really want to exit? A lot of people really don't like that and just want, yes, I want to exit, stop asking me. And they bug us about it. So if I want to know how to configure something about exit behavior, I can just do, what does the IPython have to say about exit? And I see that I've got a confirm exit flag, I've got a no confirm exit flag, and then I've got a configurable for terminal interactive shell.confirm exit. And so what this tells me is that if I started IPython, the IPython terminal with IPython no confirm exit, fit you on screen, and then if I exit, it'll quit and it won't ask me. And then this last one tells me this is something I can add to a configuration file, which I'll talk about next. This is something I can add to a configuration file so that it will always do that and I don't have to specify the flag every time. So for configuring IPython, IPython has the notion of a profile. So a profile in IPython is a couple of things. One is the first thing it is a folder. So it's a folder, and in that folder are two things. One is configuration files for customizing the behavior of IPython, and the second thing are runtime files, like your history will be in a profile, and connection files for kernels and things they all live in the profile directory, so that you can have for a different profile. Let's say you might have a profile for working on some physics project, and that will have a different history from your profile, your default profile. And so you can isolate history, and you can isolate configuration for, I want different colors, different fonts. These things can all be isolated on a per profile basis. So to start configuring IPython, we run the command IPython profile create, which will create, oh shoot, that's new. I've never seen that before. Worked this morning. No. All right. I don't know why that happened. So I can create a profile directory. That's what I get for working on Git. And that created a couple files, which you can see it created this IPython notebook config, an IPython Qt console config, and it also created an IPython config file which you can use for creating IPython. So if you want to see where these files were made, we can do IPython locate. So if you want to see where your IPython directory is, I have a custom IPython directory for the conference, so we won't actually be using any of my extensive config to confuse people. And I can set, so now I have the current profile I can access from Python by getting the IPython object and getting the location of the profile directory. So I can see the files in this profile there's my history, there are a few config files, and then there are some extra files for connecting to the kernel and this sort of thing. So I can do, if I can't. So I can look at I can look at the default config file. So this file was just generated, and it's just a Python script. So an IPython config file is just a Python script that has generated from the default attributes, the default values for all these configurable things, commented out. So you can search through this to find find the values you may want to change. So here this would be the line, and I would uncomment that and change it to false if I wanted to turn off confirm exit for all future runs of IPython with this profile. At runtime, you can change configuration with a config magic. So if we want to see what's configurable in my current session, I can just do magic config. And this shows me the current objects I have instantiated that have some config I might be able to change. And if I want to see what's configurable for a particular class, I can do config inline backend, because what I'm going to configure is the matplotlib backend that we're using to display figures. And so this has a few behaviors that we can customize, and the one that we're interested in is the figure format. So by default, IPython will display matplotlib figures as either PNG or SVG. And for some use cases, one is preferable, some use cases the other one is, and it's PNG under default circumstances. So we get, if we just create a 010 simple plot, right? That's a PNG image, so I can drag that around, and that's a raster PNG. But let's say I wanted to actually use SVG images if I want a vector image instead, which will look sharper, at least on my Retina screen right now. Maybe not over there. I can set that figure format to SVG, and now if I do the same, I can plot it, and it looks a little bit different, but that's because it's now an SVG. It's the exact same call, the exact same plot command now generates an SVG image by default instead of a PNG image. And so that's the kind of the basics of configuring objects at runtime. And so some actual customization of IPython that we can do is defining our own magic. So I'm going to start by grabbing the IPython object. This is a simple call for giving me a handle on IPython itself. And I will define a simple function. Now I can sleep for a second. If I want that as a magic, I would use IPython.register magic function. And this, I just did question mark on register magic function. This lets me register any function that I might define. So any function that you have that maybe you use a lot, or you want some you want a shortcut to something that you do commonly. This lets you define any function as a magic, and you can define it as a cell magic or as a line magic, and then you can give it a name. By default, it will use the name of the function, but you can give it any name you want. So if I want to sleep, let's try doing that properly. I can register the magic function, sleep magic, as a line magic, and we'll just call it sleep. Now I can, oops, sorry, that's, yeah. So now I can, with the magic, I can call sleep. So as an exercise, yep. Yes, so with the magic, the argument is just the rest of the line as a string. And with a cell magic, A cell magic would look like line, cell. My line was so now I've got just a simple cell magic that prints what you told it to do, and so now I can register this as a magic function, and this time it will be a cell magic, and I'll call it printing or echo. Now I can echo. This is the line. This. Right. So now, and so with magic's always the line. You get the line as text, and then you get the cell as text. And line magics are just exactly the same, but they don't get a cell. So you can actually, yeah. So there is a certain amount of ambiguity there, and that's part of why as Fernando mentioned before, system aliases might go away and be subsumed into the magics. But the main thing is that aliases are shortcuts to other things, whereas a magic is a thing in and of itself. So I think ls is an alias and cd is a magic. So because cd has extra Python logic, whereas ls just does bang ls.
Early on, the magic system would have made it clunky to really access quickly many system calls, and so I added the alias system as a separate thing. The magic system is way cleaner now, and we can get everything that aliases do now, we can do it much cleaner. So they're going to go away as a separate concept, and they'll be subsumed just into just more magics. And that way there's not one more thing to keep track of in your heads.
So with this register magic function and the ability to define your own functions, just as an exercise, I'd like you to look into making simple timers. So this is something that, you know, a lot of people like real profilers. I still find that most of my profiling is simple tick-tock, you know, marking time here and then printing the time since then at a later point. I imagine I'm probably not the only person who still does that a lot. So I would like you to try to define two magics, a tick magic that sets a time, just marks the current time, and then a tock magic that prints the time since that tick-tock, since that last tick call. So define two magics, one for marking the current time, and then another for just printing the time since that last tick call. If you want to give that a try. Then I have my own implementation of that I can show you in a sec. So I can show you secretly. Oh, no, yes. No. I guess I can't run it secretly, but hopefully load will work. Yeah, load works. And I have two implementations of this, one with simple functions and one with two methods on a class that helps coordinate the state between the two. But with register magic function, you can specify any callable will work. So my solution to this is a simple class which has a tick function, which just saves the time in an attribute, and then a tock function that pretty prints the time since the tick function was called. So then I instantiate a tick-tock object, and I grab IPython, and then I just register the magic function with tick and tock. And since their names were tick and tock, I don't need to specify anything else because the default values of a line magic with the original object's name actually works. So I will get a magic tick, and then talk, which of course is very fast because I didn't do anything. And so now, if I import NumPy, I can just do this simple loop that calls tick, and then does something that takes a bit of time, and then calls talk. So computing the eigenvalue, generating a matrix and computing the eigenvalues takes 7 milliseconds, then 20 milliseconds, and then 2 seconds once it gets pretty big. Another common thing that people do with IPython is there are often modules that you use a lot. So for instance, if you're always calling time.time or sys.argv, or if there are common modules that you use all the time, you might want IPython to import these modules as startup, so you don't have to keep typing that as your first command. To make this easy, IPython has a notion of startup files, and in our profile, if you remember, in our profile there's a folder called startup. And so we can cat the README that gets put in there by default. And it's just a folder of Python and IPython scripts. So if you call it .ipy, you can put extra logic, you can put IPython syntax in there, like calling magics and things like that. Or if you call it .py, it has to be pure Python. But what this folder is it's just a folder of scripts that are always run when you start IPython. So when you start IPython, every script in that folder will be evaluated before you get your first prompt. So this can be useful for common imports. So I'm going to write a simple imports. So these are. Yes, I sure did. Oh, this is 13.1, not 13. I didn't realize that was fixed in. Right, so I just wrote a simple file with these imports, and then let's say I use my timers a lot, so I can actually take my timers example, copy that, and let's make sure we don't rely on that. So now I can I have a TikTok magic startup file that defines the TikTok class, creates an instance of it, and then registers those magics. So now I'll have TikTok magics every time I start IPython. I'll have magic tick and magic talk available. So now if I restart the kernel, so normally I would lose those magics and lose all my imports because I just started a fresh IPython kernel. But now I have sys imported because it ran that import script, and I also have tick not found. Oh, profiles not defined. Well, I did the magics registration wrong, but anyway, you can define magics, and you can add imports, and even a common thing for your non-default profile is maybe you're working on a website or something, and you want to load up a data set or load up a database connection so that you don't have to write your initial statements of connect to the database and that kind of thing. You can have those happen at startup so that you can specify a profile that will start with the right connections. So an application of this configuration is creating a profile that runs a public notebook. So by default, the notebook has no password and it's on HTTP. But if you want it to if you want it to be accessible over the network, then you need to add a bit of security, and the notebook server supports. it's a basic level of security. So to start out, we have a password. So IPython will store a password in a config file, but since a config file is a plain text file, we don't actually want to store the plain text password. We want to store a salted hashed version of the password. So to do this, we're going to create an NBSSL profile, which generated these default config. And then we want to add this line to lock the notebook behind a password, to put a password on your notebook. But then it's still in clear text, and clear text password is not great because people can just sniff that, and that's fairly easy to hijack. So the next thing you want to do is add HTTPS, and the simplest way to do that is just this is a simple command to generate a self-signed certificate and key to serve the notebook over HTTPS. If you have a real certificate, that's always preferable, but this is the quickest way to get started to just make sure traffic's encrypted. And then the configurables in your IPython notebook config are just cert file and key file, and these are just Tornado attributes that if these are specified, the notebook will be served over HTTPS. And then the last thing is, now that it's secure, we can make it public. And then the configurable for that is just notebookapp.ip, and then if you specify star, that means, so by default this is localhost. If you add star, then it will be every interface on your machine. Or you can specify a specific public IP that you want the notebook server to listen on. And then the last config is -- no browser for instance, if you're SSHing into a machine and you want to start the notebook with on a public interface with the security enabled, then you probably don't want to open a browser, because if you're in an SSH window, the browser it will open is actually links or something. It will be something that can't actually do much with the notebook. And so you can do that at the command line with -- no browser, or you can add this open browser equals false to your notebook config. And that's the basics of IPython configuration. And I'm going to move on to,
How to start with a different profile.
So
What's profile has to create that?
So I can start the notebook. Now that I've created this profile, I can start the notebook. Profile. This would be how you start the notebook, and then browser. This would be how you start the notebook with that alternate profile. And then when you start kernels, the kernels will be started with the same profile as the notebook server. So you can add custom kernel config there. Yeah, there are plans to have multi-user. It is on the IPython roadmap, but I believe, we'll have that next year.
Work that was funded by the Sloan Foundation, but that's on the roadmap.
Yes. So we have committed to delivering that by December of 2014, but we should have something on that by July of 2014. So now that we've talked about the IPython kernel, so the notebook and the Qt console all use ZeroMQ to talk to the kernel remotely, and we've kind of abstracted the notion of performing remote execution. And with that, once you've got an abstraction for remote execution, then a logical following on that is parallel execution, because if you can work with code that's remote, why not work with more than one at a time? And so the very basics of parallel execution are when you're running in parallel, instead of kernels, you have what we call engines, which are the exact same object. There's just a different connection pattern. So rather than connecting to the kernel, the engines connect to a central controller object, and a client also connects to that same central controller, and that coordinates communication between the engines and between any number of engines and any number of clients. And I only have time to kind of show you what this looks like. And so the very first thing you want to do is open your clusters tab and start start a cluster, this will start an IPython controller and a few IPython engines. And then the module with all the parallel computing machinery is IPython.parallel. So I create a remote client, and the client has IDs. These are the IDs of the engine. So I have four engines. And then the basics of remote execution, let's say we have a function that multiplies two numbers. I can create views. So this dView is a view on all my engines. I can create a load balance view, which is an engine agnostic load balanced approach. And then E0 is a view on exactly one engine. So I have my simple function that I called locally. I can call it remotely by just taking a view and then calling apply. So it's just the exact same. Instead of calling the function, you call apply. So you just move the parentheses back and replace it with a comma, and then you've got remote execution with basic Python functions. And I can do the same thing in parallel just by using a different view that's of more than one engine. I can run the exact same function on all my engines instead of just one. Python has a built-in map function for calling a function on sequences of arguments. Views have a map method that's exactly the same. So that actually distributed the work of multiplying each pair of numbers to all my engines and load balanced across the engines, and then got the results back and reconstructed the list of results. And the API is exactly the same. So if you can express your work as a collection of map calls, you can actually farm those out remotely just by replacing the Python built-in map with a view.map method. You can also run code as strings, so it's not just apply. Ooh. What is that? Second one works. So I can just execute code. To work with the namespace in the engines, you can treat views as a dictionary. So I just assigned A to the PID of the kernel, and then I can get A back. For async results, you don't have to do blocking execution. You can submit executions and then do other work while you're waiting for the computes to finish. So here's a simple function that just sleeps for a little bit and then tells me where it happened. And that returned immediately, but get, so let's say I want to wait for 5 seconds. So that returns immediately, but get actually takes some time, and that will return when it's ready. So from these building blocks, extending that, we have magics for more conveniently doing some of these executions in parallel. So if with magic px, that's the same as execute a equals 5, but this is running in parallel. So I can print in parallel, I can get output in parallel, I can import everywhere and locally. Standard error gets colored. I can turn off blocking, so I'm doing async execution by default, and then a series of sleeps. But then px result lets me grab the result of that asynchronous execution when it's ready.
PX is short for parallel.
Yeah. Remember that the IPython engines are just IPython, so I can load Pylab mode on all my engines. Scatter is a method for taking a sequence and partitioning it across all my engines. So everybody, when I do scatter of the targets is just the list 0 to 3. When I scatter it, everybody gets one of those elements of that list. Right, so engine 0 has ID equals 0, engine 1 has ID equals 1, they all have stride equals 4. And now I can, in parallel, so px is a line magic, but it's also a cell magic. So I can, in parallel, say, don't wait for this result to finish. Generate a bunch of plots based on ID and stride, And then that returned immediately. And then while those were working, I can grab the result. And now I've got interactive plotting in parallel in the notebook. So each notebook printed some things, generated a plot, and all of that comes back to my notebook when it's ready. You get exceptions. So if your code raises exceptions, let's turn blocking back on. So when you get exceptions on your engines, you get those exceptions back interactively. So you can see, your typos, and you can see your bugs, and the engines don't mind errors and things. And also remember, since these are IPython, you can do cell magics inside the px cell magic. So I can do px bash, and I have remote parallel interactive bash. Actually, the bash is not interactive, but the interactive comes first. And this works with Ruby. Ruby's another cell magic. So you can do fairly sophisticated things. You can do, we can scatter rank again, and we can do a time it cell magic. So this is just timing, computing a norm of random matrices. And in this one, each engine, since rank is different on every engine. Right, so everybody's got a different rank. Each engine is generating a different size matrix and then computing the norm. And so that's taking a different amount of time, and I have the timings of all of those executions. And so as kind of a final demo, I'm going to show something that I tossed together, bringing this all together, bringing parallel display, parallel magics, and doing a computer vision demo of identifying faces in my iPhoto library. So iPhoto generates smallish versions of all your pictures in a thumbs directory, in a thumbnails directory, and all I did was pull those images out into a folder on my desktop, and then I'm going to find all the faces in parallel on my machine, and then display those faces as I find them. So I load up PyLab, and then do some basic imports, and then this is. So this is just some OpenCV. I don't expect you to actually have OpenCV, but this is just some basic OpenCV initialization. And these are some functions. So detect faces, this is incredibly easy with OpenCV. You just say, find some faces, and that tells me the location in the image of each face with a rectangle with the corner location and the height and the width of that face. And then extract faces just gives me a NumPy array of the sub-array of the image, of the face part of the image. So I can, and then this is just my, give me a list of image files that I made beforehand, and these are just copied directly out of my iPhoto library. And I excluded the ones where iPhoto has already found faces because that seems like cheating. So this is just a simple iterating over my pictures and then showing the result of detect faces on the first one where it actually finds a face. So that actually showed a face of a picture of a painting that I took. So now to do the exact same code in parallel, I connect my client and create a view. I run the OpenCV initialization code on my engines just like I did locally. I haven't done that on the engines, so I do that again so that all my engines are initialized with the same state. And then detect faces calls extract faces. And the way that works is it looks it up in the global namespace, but since that's defined locally, it doesn't get sent along with detect faces, so it needs to be defined on the engines. So I push extract faces to the engine so that it will be available when the engines call detect faces. And now here is a relatively advanced use of IPython parallel. I call map async, which means give me an asynchronous map result. Ordered equals false means I don't care about preserving the ordering of the results. I just, as I iterate through the map result, yield results as they arrive. I don't care about preserving the order of the results as I submitted them. And so this AMR is an async map result. So I can, with these async results, you can actually iterate through those results immediately before they're done. So I start iterating through results, and what it will do is it will wait for the next sub-element of the result to finish, and then it will yield that every iteration as they arrive. And then all I do is get the, if it didn't find anything, just wait for the next one, and then unpack the result and show the image with matplotlib if it found a face, or if it found more than one face. So if I just run this, it'll take a moment to get started, since I'm finding faces in 2,000 images. And here they come. Some of them look more like faces, some of them are, of course, false positives, but these are just arriving. Most of them are paintings. There are people. Some think that built some buildings. And you can see I've scrolled to the bottom, and then as they arrive, each time they arrive, I get a new output, and I know there's a big gap of non-found faces after this one. But, oh, here's more false positives. There's another actual face, and then some sticks. And a few more at the end. And so that's the basics of actual interactive computer vision in parallel with asynchronous execution, all with IPython in the notebook. I think that's.
Session in the next tutorial session, so we'd like to end here. If there's one or two quick questions, definitely ask us right now, but the video crew also has to be able to eat before they get ready for the next round. So if you have a quick question, ask it now, and if not, we are going to have, so first of all, there's the talk by Matt Davis that Brian mentioned about education with the notebook. Hopefully you've gotten a hands-on version of that, but he's going to discuss kind of the broader issues about teaching with these tools. And then the three of us, and Paul and Zach, are going to be manning a booth at the vendor hall throughout the week at the active conference. So for the 3 days, we are going to have an IPython project booth. So if you have questions and you want to talk in depth about this stuff, don't worry about not catching us today. You can just come to the booth and we'll be happy to talk to you there.
Stickers.
So, excuse me?
Stickers.
And we'll have stickers.
Stickers at the booth.
And we'll have stickers. So any quick questions? And if not, let's wrap it up. Yes?
To integrate, like, say, PyGal with the rendering rather than matplotlib or something. Because PyGal can export, like, it can render it to an SVG, but when I tried it, it just dumped the SVG data right into the...
Yes. So what you need to do is make sure that it's hooked up to either rep or SVG, or you use a type printer. Brian showed you how to register a specific function for rendering and that's keyed by MIME type. So you would do like SVG formatter. SVG formatter equals display formatters, and then the one that's image/SVG plus XML, and then you define a function that takes an object and then returns SVG data as a Python string. And then anytime you display that object, you will get an SVG displayed in the notebook.
Thanks, everyone.
Yep.
Is on the I, right? The I in IPython is for interactive because all of the tools we're building are meant to be used with a human in the loop. So if you go to our website, the installation link should have given you the instructions that you needed. Hopefully by now everyone is okay with that. I want to point you to a couple of important links. We won't have time to dive into them in detail, but at least I want to highlight them for you. And that's these two links, our example collection and our notebook gallery. Our notebook gallery is actually a wiki to which you can contribute. Which is a list, a growing list of interesting things that people are doing with the IPython notebook and notebooks that they're building in all kinds of areas and fields. And because this is a wiki, you can add to it. I'm not going to go over all of them, but just to give you a very brief taste of what one of them looks like. This is the first chapter of a book on statistics and Bayesian inference. And this is what a notebook can look like. It actually looks like a book with math, with very nice typesetting. But you have code, you have mathematics, you have code, you have the figures right there. And every one of these notebooks at the top has a download link that lets you download it and execute it right away. These things are all powered by a web service called NBViewer, which is part of the IPython project. And NBViewer is effectively a Heroku-based app that will convert your notebooks and put them up on display in HTML. So what this enables you is to share notebooks with others, so that you can put a URL here of any publicly available notebook and share it. And that's how the gallery is basically a long list of links to NBViewer-powered renders, and the server re-renders the notebook when it's requested with a short caching period, so that as people update their things, whenever you visit them from here, you get updated versions. And one of the important links in here is actually our collection of notebooks from our official documentation. This is a collection of notebooks that will cover some of the things that we're covering here in a lot more detail and with a lot more explanation in depth. So I strongly encourage you later to visit these. And whenever you click on any one of these links, this is part of the official IPython repository, but whenever you click on any one of these links, what you get is precisely the rendered version. If the network cooperates, what you get is precisely the rendered version of that particular notebook, so that you can read it and study it. And so these are links that are useful to know about. Okay? So at this point, everyone should be set and ready to go. Again, the tutorial location is IPython in depth on GitHub. This is where the materials are. And you can either clone the repo or you can download this zip file and unpack that zip file wherever you want it to go. Is anyone having a problem? I'm sorry. Okay. So, and we have it on a USB stick if somebody's having connectivity issues. So the first thing that you'll want to do, and now I want you to follow with me, is go to the directory. Whoops. Go to the directory where you have the unpacked this zip file and cd into the notebooks directory. For those of you on Windows, you want to be using the command.exe shell. If you have a git bash shell, it may not have your paths configured correctly. So use command.exe. On Linux or the Mac, just go with the terminal and simply type IPython notebook. Okay? And if you type that, something like this should happen, where with no error messages, and then it will tell you that the notebook server is running on your local machine. It's not listening on a public port, so don't worry about security. We'll cover that later. So it's completely confined to listening on your local machine only, and on that port by default, and it will most likely actually open the browser. In my case, I have it configured not to open it by default, so I had to open it myself. And once you open it, this is what you will see. And so I am not going to cover in depth what all of this is right now, because the in-depth usage of the notebook is going to be the second part of the tutorial. What I'm going to do is we're going to start using it to see where does IPython go beyond plain Python. Because what IPython does is really go a little bit beyond what the plain Python experience is. And so what IPython will do is actually go and dig, using the fact that the language is highly introspective, it will go and dig into the collection's named tuple object, and maybe I should just full screen this so that we have a little bit more space. It will dig into the collection's named tuple object and show me where was it defined, what is the file, what kind of object is it, what is the file where it was defined, what is the calling definition of the object if it's a callable object, and furthermore, it will show me the docstring of the object. So this is one of the reasons why in the scientific Python community where IPython was born, we tend to put so much emphasis on high-quality docstrings. The standard library has a very uneven coverage of docstrings. Some of them are pretty good, some of them are very minimal or non-existent. And part of it is because we use this a lot. As we're working, we just type object question mark, and right away it tells us what's going on. And if you add 2 question marks, IPython will try to actually dig even deeper into the object and give you more in-depth information. So if I ask double question mark, instead of giving me a summary of the main properties of the object like type and signature and docstring, IPython will actually show me the entire source code for the object, and it'll syntax highlight it. So now when I type collections.counter double question mark, then what we have here is the entire source code for that particular object. And you can actually ask for the source code of any specific object. So for example, the counter, the most common method, if I had asked for counter.most common instead, then I would get the source code just for that method, right? So it's a very useful way of understanding, for any object for which the source code is available, it's a very useful way to quickly learning about your libraries. The way I learn about most libraries is not by reading their documentation, is by just asking with question mark for the methods and functions that I'm interested in, that quickly can learn their signatures and see their code and just move along. So it's trying to be very effective in its workflow. And finally, there's a way of using the question mark for querying namespaces. So if you want to find what variables do I have currently defined that have int in their name, you can use the kinds of globs that you use at the shell, like ls star, but with a question mark, and then what IPython will do is find any names that match that pattern. And you can do this within a namespace, or you can do it at the top level namespace. So it's a very useful way of digging into big libraries that you don't know to find bits and pieces of information. So this is basically anything that has the letters I and T in my namespace. These are the things that have that. So these are the basic tools for digging into objects and using the IPython introspection machinery. If you want to learn a little bit more about all of these special syntaxes, you can type at any point %quickref, and quickref will open a quick reference card of all of these special syntaxes. I'm not going to go over them. We're not even going to cover all of them today, because IPython has a lot of syntactic tricks that are really meant to kind of speed up your workflow. But at any point, if you type %quickref, you will see a little help page like the ones we're seeing with a quick reference card that is it's basically like a cheat sheet for the system. Okay? Any questions at this point? So, yeah. Excuse me? They do up to a point. The problem is there are no hooks for finding the source code of a native code object. So you will only get very basic information, the kinds of things that the inspect machinery can find, but not the source code, with one exception. For Cython-based extensions, we can dig in. If the source code is still available for Cython-based extensions, we can find a little bit more information. But for normal extension modules, it won't, because it's just binary. And if it was compiled, I mean, Python doesn't leave source information behind for us to find. So there's just not, it's a binary blob on disk, and there's nothing we can do about it. It will give you the doc string if it has it. It'll give you the high-level information like name, docstring, from where on the file system it was imported from. So you'll get a little bit, but you won't get as much as with pure Python. Any other questions? Tutorial. My name is Fernando, and I'm going to be the first lecturer this morning. But the three of us from the IPython project are going to be taking turns. So Brian Granger and Min Reagan Kelley up front are also here, and they'll be taking relief from me a little bit later. And we also have in the room two other members of the project, Paul Ivanov in the back, who is a grad student at UC Berkeley working with me, and Zach, I'm sorry, Zach, your last name? Sather. Zach Sather, who Saylor, who is a student with Brian Granger at Cal Poly San Luis Obispo. All four of us will be available to help you. If you get stuck on anything, just raise your hand, and the nearest one of us will come and try to give you a hand. Needless to say, feel free to interrupt us while we're speaking. This is meant to be very interactive. Before we dive into our tutorial, I'm going to take a couple of seconds to show you a few slides that were sent to us by Stuart Williams, your tutorials Uber coordinator for the entire conference, who asked that we pass along the message that the conference still needs volunteer help for a number of tasks, and there are a number of fairly low commitment opportunities for you. There's ways for you to help, bagging swag on Thursday, helping at the registration desk anytime. But on Friday, you meet lots of people. And there's a couple here. If you go to that URL, bit.ly, PyCon volunteering status, you can see exactly what they need and how you can help. So if you can spare a couple of hours to give a hand with one of the tasks for the conference, please do so. OK, so we're going to get started with a very quick introduction and quick check of installation status. So we've been doing that kind of informally for the last 20 minutes. We're not going to really have slides per se. This is going to be all very hands-on and meant to get you really exercising your fingers and building muscle memory and learning how to use the tools. So the only introduction that I'm going to give really to the project is straight off of the website. And what I want to point out are a couple of kind of broad ideas. The first one being that IPython is really a system for interactive computing, understood in a very broad sense. Yes, it began as a command line replacement for the default interactive Python shell, but the scope of the project has grown beyond that. And in reality, today, we think of it as an architecture for interactive computing that allows you to use any language for which it's sensible to be used interactively, so that you can drive, and we're building an architecture to allow you to drive actually processes that are implemented in other languages. We already have a Ruby backend for the IPython architecture. We're building a Julia backend. There's a MATLAB backend in the planning. There's an R backend in the planning. So the idea really is to provide the interactive workflow that is very common and very necessary in many fields of computing through the same common messaging architecture and with the same protocols and formats for storing those interactions, which is the notebook format that we'll come to later. And so, yes, if you are a dyed-in-the-wool Python programmer who does nothing but Python, IPython will continue to serve you well. But if in your work and your needs cross language barriers, there's actually a chance that some of the tools we have here will be useful in that regard too. And we don't have a ton of time to dive too much further in that direction, but it's important for you to sort of understand the scope of the project. And so what IPython provides are, first of all, the classic interactive shells that we've had for a long time at the terminal, and we also have a Qt-based shell that I will very briefly demonstrate that is basically a terminal on steroids oriented towards interactive computing. We have a browser-based notebook that we'll be using extensively throughout the presentation that you'll see a lot. IPython has support for synchronizing with event loops and therefore synchronizing interactive applications with GUI applications without blocking the interactive control. And we'll see how to do that. That can come in very handy in many situations. IPython is very easy to embed in your own Python codes so that you can have either an interactive shell pop up in your code or actually an interactive network controlled engine, and we'll see how to do that. And finally, high-level tools for distributed and parallel computing that can be used interactively as well. The emphasis is always, if you click on this notebook, IPython Beyond Plain Python, you should see right here what our first notebook is. Can everyone in the back see? And is this font size going to be OK for the recording team? Or should I try to crank it up further? Obviously, the more we crank it up, the more space we lose on the screen. But if it's unreadable, then there's no point. It's OK as is? OK. Actually, Min, excuse me? Yeah, that would be actually probably a good idea. Does anybody know how to dim maybe the front lights? Because it is true, they're washing the screen out a lot. Min, do you have it rendered on an iPad, this one? by chance? Do you think you could get it off of NBViewer? And maybe I can use it as a cheat sheet. So what I want you to do is type with me. Yes? Paul, can you try to help him? Yeah, Brian and Paul will give you a hand. Back to where I'm going to restart what I was doing. So I am in the directory where the notebooks are, and what I need to run is IPython notebook, and that will give me something like this, which then I can go and open my web browser to this dashboard running on my local port. And so the first thing that I want to go through is the notebook that basically covers where does IPython go beyond the plain Python experience, okay? So IPython is meant to let you do everything you would do in a Python shell is valid Python. So if you type normal code, it should execute just like Python code executes. But there are some things that IPython does that are not valid in a normal Python shell. And we're going to try to understand what is it that IPython offers beyond the plain Python shell. So when you're in the notebook, if you type a block of code, like say print hi, in order to execute code, you hit Shift-Enter. So that's how you execute code in the notebook. So I want you guys to follow along with me and basically start getting used to the muscle memory of typing code in these cells and executing it as we go along. So Shift-Enter is what executes code, and the reason why it's Shift-Enter is because these little areas are not like a terminal prompt. They're more like a mini text editor. So you can put more code in here and hit Shift-Enter, and it will execute all of the block as a single chunk of code. So you can also execute with Alt-Enter. I'm sorry, Alt-Enter is a newer feature for those running the development tree. You can also execute with Control-Enter, which does not move the cursor in case you simply want to try something here and replace it later with something else. If you run Control-Enter, the cursor stays in the current cell. With Shift-Enter, it moves to the next cell below. So that's code execution, and that'll be the same as plain Python. Now, if you want help, IPython has added a special syntax which isn't valid Python, and the most basic version of that special syntax is to just type question mark. So when you type question mark, what will happen is you get a little pager here at the bottom. And this pager basically shows you additional information, and this will work the same thing in the notebook. If you're in a text terminal, it'll use the system pager, but it'll always try to find a way of displaying information for you. You can dismiss this pager by clicking on the divider. And so when you type simply question mark, IPython will give you a very basic introduction to what it does. Okay, this is basically what does IPython do, and you can drag this divider if you want to read it a little bit better. So I'm not going to read through it because the whole point of this meeting is to cover some of this for you, but a simple question mark gives you information just about IPython itself. But the question mark operator is actually an operator that you can use at any point. So if I type import collections, and then I want to find out about what is the name tuple object, if I type collections.nametuple question mark, all right, do interrupt at any time. So when you're working interactively, the basic workflow, as I said, is the same as Python. You type two numbers, you add them together. The Python shell always creates a little variable called underscore. We still have that same variable. However, you can, if you want, you can suppress output by putting a semicolon at the end of a line. And if you put a semicolon at the end, no output is generated and the underscore variable isn't updated. So in this case, underscore is not 30, it's still the old 22. The reason why that's useful is because there are many libraries that when they do a computation, they also generate a lot of extraneous results, especially things like plotting libraries, which for some of us are very important. They also produce a lot of stuff. So we often get into the habit of putting a semicolon at the end of the last line so that we only get the figures, but not the actual return values of the underlying object. So it's just a useful trick to know when you're building, especially when you're building these documents where you just want maybe to compute something and leave the figure for people to see, rather than leaving a bunch of internal object pointer addresses that aren't meaningful. Now, these prompts out here on the left that say in and out, they are obviously meant to give you cues of what you've been doing and in what order you've been running code, but they also actually exist as variables. So we do create an underscore variable, but we actually create underscore and a number for any variable that I have created. There is actually an underscore and that number automatically created for you. So underscore is the previous one, but underscore and the number will give you whichever old one. The reason why that's handy is if you've computed something that took a while to compute and you have that result, but you forgot to assign it to a variable, no matter. As long as you can read which number it has, you know that there's underscore and that number auto-generated for you. And they actually are also stored in a variable called out with a capital O, which is effectively a dict of outputs. Now, the reason why we create the automatic underscores is because you might clobber the out variable with one of your own variables that you call out, and so we have these automatic ones. And we have a single underscore, 2 and 3 underscores, actually, for the last and the two back. These things come handy when you're just doing quick calculator-style work. And similarly to the outputs, we have input variables. So similar to the output, we have in variables and underscore I variables, which means that you can manipulate everything you've done with your inputs and your outputs programmatically. You can re-execute based on these input lists or output lists. And there's a command called %history that will give you that will show you what your history is, and it has a number of options, such as, for example, if I simply type history, it'll show me everything that I've done so far. It'll print my history. It's useful if I want to copy it to into a text editor, for example. But I can say, show me my history with line numbers. If I do -n, it'll print it with line numbers. Question?
Is that used only interactively, or would you ever use that code?
No, that's used only interactively. So that's a very good question. That underscore syntax only makes sense interactively, and the reason why it only makes sense interactively is because those variables are created when sys.displayHook triggers. And sys.displayHook is something that only triggers when Python is being used interactively. When Python is being run in code, code execution doesn't trigger sys.displayHook because the code objects get compiled with a different set of flags internally. And so it's actually something that hooks pretty deep into the Python machinery itself. And so those things don't even exist. When you're running a script by itself, those things don't even exist at all. Good question. Yes?
When using the shell like outside of the notebook, might doesn't make sense here, but the history, is that preserved like over sessions?
Yes. So if we ask here, as always, the question mark, right? So history question mark. And history shows you how you can actually access the history of other sessions. There's a special syntax to access the history of other sessions. And in